and welcome to this course on using generative AI for data management and data remediation. What we are going to explore throughout this course is how to use generative AI models, such as text generative models, such as LLMs, to help you automatically perform certain data-related operations with the goal of increasing the data quality of your data sets. So we're talking about, for example, detecting schemas, doing data profiling, data remediation, transforming data sets, and a lot more. Let's take a moment just to cover the main objectives and modules in this course. Hello, and welcome to this course on generative AI for data management and data remediation. In this course, we are going to cover how to use technologies such as generative AI models, namely text generative AI models such as LLMs, to improve data quality, to do data profiling, remediation, and other tangential activities. What are our major learning objectives in this course? Some of our major goals. One of these goals is to understand how data quality, the data lifecycle, and generative AI work. That is a quick recap of the fundamentals before we dive deeper onto more complex operations, or how generative AI can help at the data creation or data ingestion stage. That is when you are receiving data in real time or creating them. What can Gen AI do? Well, we can complete values, we can extract schemas, we can annotate data, and a lot more. Or for example, how generative AI can help actually remedy data and increase their quality, be it by cleansing noise, augmenting the data, detecting anomalies, and performing preliminary statistical analysis, among other operations, that is to actually remedy and improve the quality of data. Or how generative AI can help at the data transformation stage when you want to transform them, change their format, change your schema, and so on, by detecting the schema that exists, both the source one and the target one, by mapping the fields from one to the other, or by actually transforming data sets using generative AI, for example. Or how generative AI can be integrated in real-time pipelines in a programmatic manner, for example, automatically correcting data, transforming them, and so on. Instead of actually posing a query to the LLM, for example, and obtaining an answer in real time, we integrate it in a programmatic manner in some sort of pipeline or script so that you can automatically, for example, obtain the data, then use generative AI, a specific LLM, to correct errors in those data, and then integrate them, for example. In other words, automating the use of generative AI. Or, for example, how to use RAG, or Retrieval Augmented Generation, which can enhance LLM answers at the various stages. That is, if you have documentation, for example, that provides more context for a specific dataset, then you can use that to increase the quality of the remediation efforts or annotation efforts for that specific dataset. For example, if you're trying to annotate additional data or increase the quality of data for specific transactions, if you have documentation about those transactions that provides more context, then you can use those in RAG so that the answers are augmented in a way and provide more accurate information. And in terms of modules, how many modules are we going to have in this course? Well, we are going to have 6 major ones. The first one is about the fundamentals, right? It's about the basics. What are the basics of data quality, data remediation, and generative AI? You can skip this module if you already know a lot about these areas, but it's always good to have a quick recap before we dive deeper onto all of these topics. Then the second module is going to be about Gen AI in the data creation or ingestion stage. That is, what can Gen AI do for us at this stage? Completing data, creating data, synthetic data themselves, extracting schemas, and a lot more when you are receiving the data or creating them. Then module number 3 is going to be about data remediation with generative AI. That is, using generative AI to clean data, to standardize and cleanse, to debias, to just analyze data and profile them, or to augment them and annotate. Then, module number 4 is going to be about data transformation with generative AI. That is, using generative AI to map schemas, to generate metadata, to define validity rules or business rules for those datasets, and more. Then, module number 5 is going to be about real-time integration. That is, by this point, we will have covered how to use generative AI in a manual manner, right? Copy-paste the dataset together with a specific prompt, for example, and obtain an answer. But here, we are going to cover how to integrate generative AI, ideally in real time in various data pipelines, with some sort of script where you call the LLM, such as a function, and you use those results in an application itself in an automated manner. And finally, our 6th module is going to be about RAG, or Retrieval Augmented Generation, for data quality. That is, we are going to cover how to use RAG to empower generative AI use at various stages. How can you use additional documents that provide additional context and information and help keep hallucinations in check, to remedy data, to cleanse data, to transform data in terms of schema for all of the stages that we've covered in the other modules. So as you see, this course is going to be all about using generative AI models to help you automatically perform data-related operations, but specifically with the goal of increasing data quality. Welcome to this module about some fundamentals. In this module, we are going to cover some basics of data and generative AI before diving deeper into these more advanced topics. So we are going to cover a summary of these different disciplines just as a recap of knowledge, if you will. Let's take a look at the topics in this module. Welcome to this fundamentals module where we are going to cover some basics of data, data quality, and generative AI. So in this module, what are we going to focus on? Basically, some fundamentals and some foundations of the topics that we are going to talk about in higher depth in the following modules. For example, we're going to cover what are the basics of DQ or data quality, how is it measured in terms of the various dimensions, and how we can improve that data quality with various operations such as data profiling, remediation, and other ones as well. Or, for example, the basics of the various stages of the data lifecycle, creating data and ingesting data, remedying data if they have low quality, transforming data, using those data, archiving them, disposing them, and possibly other stages as well, including where specifically at what stages can we intervene with generative AI to increase data quality. That is, where in the data lifecycle does generative AI have the best use? Or, for example, the basics of what is generative AI itself, namely text generative models, such as LLMs, such as ChatGPT, for example, that we can use. But in this case, naturally, we recommend open source and not ChatGPT itself, but that family of models, specifically how they can help us increase data quality. That is, how to use text generative AI models to increase data quality. For this purpose, in this module, we are going to have 3 key lessons. The first one is about the fundamentals of data quality and remediation. That is, what are the basics of what is data quality? What does high data quality mean? What are data quality issues? And so on. How do we actually increase data quality? And the usual tasks associated with remedying data or increasing their quality. Then, our second lesson is going to be about the fundamentals of the data lifecycle. That is, what are the major stages that data go through from the moment that they are created or ingested up to the moment that they are discarded, and how generative AI can intervene in each one of these stages, when you are creating data, when you are remedying data, when you are transforming data, and so on. And finally, we'll have a lesson on the fundamentals of generative AI, with a focus on text generative AI. That is, what is generative AI itself, such as LLMs for text, and what they can do for us in terms of increasing data quality, but also what they can't do, the risks and limitations as well. So as you see, this is a module with some basics in terms of data and generative AI before diving deeper into more complex topics that use this knowledge. Let's talk a little bit about data quality and remediation. If you are a data professional, you may already be familiar with a lot of these concepts, but we have to touch on what is data quality, what are the dimensions for data profiling, what is data profiling itself, data remediation, and other basic concepts related to fixing data, if you will. Let's take a look at these. Welcome to this lesson on some fundamentals of data quality and data remediation itself. When we are talking about data remediation, one of the core concepts that we need to understand is data quality, also known as DQ. Put simply, data quality indicates the degree of quality in a specific dataset. It is self-explanatory to a degree. In other words, data that have high data quality can be used, while other data that have low quality usually can't be used. But it's important to understand that high or low quality is not absolute. It's usually according to one of the key dimensions used in data profiling, for example, which can be completeness, accuracy, and so on. For example, having high data quality according to the completeness dimension means that data are complete. For example, if you have missing entries or financial transactions that don't have a value, then those are not complete. They have low data quality according to the completeness dimension. Another dimension is accuracy. For example, if you have a set of values and the values filled, but those values don't make sense, then they have low quality according to the accuracy dimension. But if they have values that make sense and they are correct, then they have high data quality according to the accuracy dimension. Then you have all other types of dimensions, such as, for example, timeliness, right? Do we have data that are timely and that are updated, or are they not updated, right? High data quality or low data quality according to that dimension as well. And this is important because high data quality is not always the same. A data set can have high data quality for a specific purpose and low data quality for another purpose, right? For example, if you have a data set where all entries are filled, but all of the values are bogus, then it has high data quality according to the completeness dimension, because all of the values are in fact complete. But it has a low data quality according to accuracy, because none of the values make sense. So it's important to understand data quality in this concept. It's always attached to a specific data dimension. And there are 2 key disciplines that help maintain high data quality: data management and data governance. Data governance, for example, focuses on the policies, on the data validity rules, and others to begin with high data quality in the first place. The goal is that you never even have to fix the data because the data already come in with high data quality. But then you have data management that focuses on actively performing remediation to fix low data quality. So in other words, data governance has the job of making sure that data with low quality don't even enter the organization, while data management takes the data that do have low data quality that already enter the organization and aims to fix them. So data management is more direct. It's about being hands-on and fixing the data, while data governance is more indirect. It's about setting general policies and rules so that this never even happens in the first place. In going back a little bit to the dimensions, it's important to understand that the various types of data quality issues that you may have in various datasets usually correspond to the dimensions that exist. So for example, if we have completeness, data quality issues related to completeness mean empty values, right? Low data quality in terms of completeness means that the values are not complete. They are missing data. If you have a dataset with missing entries, for example, it has low data quality in terms of completeness. Then we have, for example, accuracy, right? Low data quality in terms of accuracy means wrong or inaccurate values. They may be complete, but the values don't make sense. For example, financial transactions where you have a price that is negative or that is zero, for example, if that is not justified by specific business rule or exception, for example. Or consistency, right? Low data quality means that multiple repositories of data have conflicting values for the same data. The data are not consistent across repositories. Or, for example, timeliness, right? Low data quality, according to timeliness, means that the data are not updated. They have information that is outdated and that doesn't make sense anymore. So anytime that you have a data quality issue in your organization, usually it's going to be attached to one of these dimensions, right? For example, hey, we have an issue where a lot of the customers in our data set don't have a lot of their personal information filled in. That's a completeness issue. But for example, you may have a situation where you have an IoT sensor and there was some sort of issue, so the temperatures for a given period don't make sense. That's an accuracy issue. So usually, data quality issues are attached to a specific dimension, which also informs how we are going to address that data quality issue as well. And we may also have, besides these standard dimensions, other ethical dimensions. So for example, fairness, privacy, consent, or others. For example, does a dataset have high quality according to the consent dimension or not? These data that were collected, did we obtain consent from the person or not at all? Or privacy, are we keeping these data secure in terms of how sensitive they are? Or are they even classified in terms of sensitivity? We can have high data quality or low data quality according to those ethical dimensions as well. A lot of organizations don't use them, but they are becoming more popular as data governance becomes more present in organizations. When we talk about data remediation itself, usually this is done by a data management team because it's an active remediation effort. It has two major components, which is the profiling, finding out what are the errors that exist, and the actual remediation, fixing those problems. So the first step is profiling, or data profiling, where we detect the issues. So what we usually do is we apply a statistical model, for example, to find biases or overrepresented values or outliers or other unusual patterns. And it's important to understand that in some cases, these can be justified or they may not be justified. For example, if you have purchases in a department store and you have a peak in terms of purchases in the holiday season, you do have outliers, but naturally those are justified. So it's important to understand that when we find errors, we are finding possible errors, right? Certain outliers or certain overrepresented values may have a justification. And there may also be other sorts of issues, right? We may check for unenforced rules. For example, we may have a data validity rule that says every customer must have an associated address. And we find out records of customers that don't have addresses, right? So that's a data validity rule that is not being enforced. Or we may just find some obvious problems, right? Such as duplicates or empty entries or things that don't make sense immediately when you look at them. But either way, we find out what is the issue through one method or another. And then we have another stage, which is the remediation, right? We address the issues. After we find out what the issues are, we have to actively address them. So we may use methods to estimate values to replace values that are missing or incorrect. For example, if we have a set of transactions that don't have a transaction value, can we obtain that information in some other way or estimate it to fill those values? And how well can we estimate those values? Or we may cleanse and standardize data that have the wrong format or that have noise, right? We may have, for example, lists of codes or values for enumerations that don't use the same enumeration across different datasets. For example, a list of countries that in a dataset are represented by a numerical code, and maybe in another dataset they use an abbreviation. So you cannot integrate both datasets and you have to standardize those values. Or other types of issues may involve removing duplicates or merging values or records or replacing references to values that may not exist, or the reference was not updated and they now exist in a different record, for example. So as you see, we have a couple of important concepts here. We have to understand what is data quality, that data quality is evaluated through a couple of dimensions, and that we also perform data profiling and remediation at different stages in order to fix data, if you will. Let's talk about some basics of the data lifecycle. It's probably no news to you that data go through multiple operations throughout their lifecycle. They are created, they are used, they are transformed, they are archived and destroyed, and more. But what we're going to focus on in this lesson is how GenAI and automated remediation, if you will, using GenAI can be applied to that data lifecycle as well. So an overview of both of these. Let's take a look. Welcome to this lesson on the fundamentals of the data lifecycle, where we are going to cover the various stages that data go through in an organization and how GenAI can intervene at these. It's no news that data go through multiple stages in our organization from the moment that they are created or at least acquired by the organization in some way, integrated, up to the moment that they are destroyed in a permanent manner. So we may start by creating or ingesting the data, right? Either we create the data ourselves or we integrate them from an external source, but it is the moment that they enter the organization officially. So we obtain the data in some way in general. Then those data are stored in the organization, either directly after they are created or ingested, or we may apply some pre-processing, but in some way we have to store the data in the organization so that we can use them later. Then we have data cleaning, remediation, and improvement. That is, after we store the data, we improve their data quality in some way. Ideally with EG, what you want to do is you want to acquire data that don't even need to be fixed in the first place. But if you do store data that need to be addressed in some way, this is where you do it. We acquire the data, we store them, and then we treat them for the issues that they may contain. Then we have data processing and or utilization. We have to use those data in some way, right? Because otherwise it's no use to have them. This is not a focus of this course. We are mostly focusing on remediation, but this is a stage, right? You may use those data for reports. You may use them for data science. You may use them to actually create or edit other records. You may use those data for whatever use case you may have for them, right? You use them in some manner. And then we have data archiving or disposal. That is, if we don't need the data immediately anymore, but we still want to keep them in the long term, or because we need to due to regulation, we may move them to another permanent storage that is not as immediate, such as a data warehouse. Or if we don't need the data anymore, we don't need to retain them, we may permanently delete the data. This is the final stage. To increase data quality, we are going to use text generative AI at very specific stages of this lifecycle. For example, at the data creation or ingestion stage, which is the first point of contact with the data, we may do things such as gathering, standardizing, or cleansing the data, right? Generative AI can help summarize, can help detect schemas, can help even remove errors or correct errors, and so on. So we acquire the data in a better manner, if you will. The data are going to have higher quality to begin with because generative AI is used for that purpose. Then, at the data policy and rule definition stage, that is, after we have acquired the data and we have to ask what are the validity rules or the business rules or the data sensitivity levels, access control rules, and other policies and rules that may apply to these data, we have to create these. How can generative AI help? These rules and policies are either immediately defined when the data are acquired or shortly after. When we want to use them, we need to have these rules in place. So it can be a lot later than after we ingest the data or create them. But generative AI can help create those validity rules and policies, such as for access control, for data retention, what is the regulation that applies here, and so on. This is interesting because, for example, if you feed documentation about your business practices and others, then generative AI can create specific business rules and data validity rules that take that into account. So it can really accelerate this stage. Then another stage is data remediation, actively fixing problems themselves, right? We fix data that have issues. And generative AI here can help in the traditional manners just faster, right? It can detect issues, it can enrich data, it can change values in data, it can change formats, it can cleanse and standardize various values, and so on. So it can do a lot of what we already do in terms of profiling and remediation, but in many cases faster in taking more information into account. Then at the data transformation stage, which is when we have to reshape or restructure data. For example, if we want to integrate a data set with another data set, or if we are just changing the schema of our databases or data repositories, we need to transform a specific data set or all of them, right? And generative AI here can help detect schemas, both the source one if it's not documented, but also the target one. It can map fields that is in the source schema and the target schema. What is the mapping between these two fields? and it can help convert the data themselves according to those rules. So it can both help define what are the parameters for this transformation and also execute the transformation itself. And ideally, we want to build pipelines so that we can use generative AI in an automated manner for every single one of these stages. And we are going to cover these in more depth in module number 5 about the pipelines themselves. But to give you some examples, for example, at the creating or ingesting data stage, we can have a pipeline of, for example, automatically gathering the data and structuring them, automatically cleansing those data, and automatically running preliminary checks, such as data profiling with statistical analysis using generative AI. All of this in an automated manner, so that the data that come in are already filtered in a way in terms of high data quality. Or for example, for defining policies and validity rules, we can have a pipeline such as automatically detecting new data in a repository, automatically calculating the sensitivity levels for those data based on the personally identifiable information that is contained in them, and automatically generating access control and data retention policies, for example. All of these done automatically with generative AI. Or, for example, a simple pipeline of detecting new data and automatically calculating the data validity rules, right? For example, if you have a price field, then the price cannot be lower than 0, and so on, for every single one of the fields detected. Or, for example, for the remediation stage, we can have a pipeline such as automatically detecting issues in a dataset, then automatically filling in the missing values or wrong values with some sort of estimation procedure, and then annotating the changes. For example, creating a new column that says, how is this value generated? Did it come with the data set to begin with, or did we estimate it with generative AI? In other words, labeling what were the original values and which were the ones that we generated ourselves, if you will. Or another pipeline could be automatically detecting a bias, then automatically resampling the data set to cut a little bit of that overrepresented portion, or increasing the sampling of the underrepresented portion, and then rerunning bias detection to make sure that we actually fix the bias. Or at the stage where we are transforming the data, we could, for example, automatically detect the schemas of a given dataset, map the fields from one schema to the other, source to target schemas, and then perform the conversion. So as you see, we have a couple of common operations in the data lifecycle, as well as some where GenAI can really help us, be it by structuring data, by creating automated validity rules, policies, and so on. So we have to make use of GenAI at these specific points. And ideally, we want to create automated pipelines that use GenAI for multiple processes in sequence to perform all of this without human effort, or with human effort being optional. Let's talk a little bit about generative AI. When we're talking about data-related operations, usually we focus on text generative AI, such as LLMs, which is the family of models that ChatGPT, for example, belongs to. What we're going to cover in this lesson is what are the capabilities, the drawbacks, and some ways to mitigate those drawbacks, such as by using RAG when using text generative models for data operations. Welcome to this lesson on the fundamentals of generative AI, namely text generative AI, what it can do and what it can't do. Generative AI is disrupting various industries. One could argue the whole world. And this is not clickbait or cliché, right? It really is true. But in essence, what is generative AI? Well, it generates new data, right? It stands in opposition to what we call discriminative AI, which draws conclusions from data, right? So discriminative AI models usually draw some conclusion from data. They classify, they perform regression, clustering, and so on. Generative AI models are a little bit different. They don't draw conclusions from data, they generate new data, right? So we have generative AI versus discriminative AI. And generative AI exists for text, audio, video, image, and possibly many other formats, right? Anything that you can train a model on, it can generate new data for that specific medium or that combination of elements. But we mostly care about text models such as LLMs, because when we are transforming data, it's mostly going to be a text generative model, right? You copy paste the dataset together with the instructions of what to do for that dataset, and possibly you use support documentation or other sources of text, and then it performs some operation on those data. Now, generative AI models such as LLMs can perform a myriad of tasks related to data, right? They can identify issues, they can flag biases, they can perform checks, such as performing preliminary statistical analysis, just finding out what seems wrong about a dataset at first glance. Or for example, they can also transform the data, they can restructure the data, they can remove noise, they can map fields, they can change specific values or specific codes for a specific field, and so on. Or they can just summarize data, enrich those data with additional information, or augment those data in some other way, right? They can take values that already make sense and enrich those data with additional information. and so on, right? Possibly any task that you can think of related to data can be performed by text generative AI model. But naturally, you have to give it a specific context and specific indications. For example, if you are detecting a target schema for transformation, you have to know exactly what are the criteria for that target schema. Is it already defined by the repository that we are moving the data to? Do we have some freedom? Do we want to transform something specifically about the data? And so on. Whatever task you want to perform in terms of data, it can usually be performed with a text generative AI model, but you have to know exactly what you want to do and what are the parameters for that. Now, when using these LLMs or text generative AI models in general, there are things that we have to keep in mind. For example, one is computational intensity. They use a lot of resources, right? Especially if you are using a locally hosted open source solution, it's going to consume a lot of computational power. And this may not seem like an issue when you are just performing one operation. But as soon as you want to integrate one of these LLMs in an automated pipeline, for example, a pipeline that automatically detects new data added to a repository, automatically identifies issues, performs remediation, and then dumps those data, as soon as it becomes automated, then the computational power becomes an issue. Or it may be the case where you can run the LLM, but you can't run it fast enough. So something that would be real time is not real time anymore, and that is not enough for your specific use case. Then speed and scalability issues. A little bit of what we talked about, right? Things may slow down. So certain tasks that you could do in an automated manner, such as acquiring data, now you can do them in an automated manner, but it's not going to be as fast. And as soon as we start talking about large quantities of data or even big data, then scalability can become an issue and LLMs can actually become a bottleneck. Then we also have hallucinations, right? Remember that LLMs may invent wrong or false facts. They tell you what is probably true in every situation, but in certain cases, such as, for example, counterintuitive situations, they may invent something that would probably be true, but just is not true in this case, right? And when you are using LLMs for data remediation, hallucinations can be wrong values, wrong rules, context degeneration, and other types of issues. And then, as a great segue to the previous point, context degeneration itself, right? So subsequent answers to the same request may obtain different results. Because as the context window slides, the LLM starts forgetting the first things of a conversation and starts remembering additional things from recent answers. So you may have a situation where in the same LLM for the same conversation, you are remediating 10 different datasets, but the way that it's performing remediation on dataset number 10, estimating the values, is not the same way that it used for dataset number 1. Because as the conversation evolves, it starts to take different things into context and it starts to forget other things. Right? So you may have a situation where different data sets are estimated or different errors are fixed in different manners because the context changes between those operations. Of course, there are ways to mitigate this, but it's important to keep in mind. And then we also have lack of transparency, right? You don't always know exactly why something was changed or generated. Because LLMs work with text patterns, there's no transparency. For example, if you're doing data profiling and you detect an outlier, you know exactly why that is an outlier with statistical analysis, right? You know, hey, this is the distribution of values and this value doesn't fit the distribution. But if you use an LLM, why is that value an outlier, right? You can know it intuitively, but you don't have a justified answer for every error that is detected or every operation that is done, right? Or when you are generating values, for example, for remediation, why did the LLM generate the specific value? We don't know, right? It's some sort of association between the text patterns of information that seems like this specific text pattern, but you don't have a usable justification, right? You can say, we multiply this factor by this probability, and this is the value. You don't get that with an LLM. Then we also have another issue, which is more subtle, but which is language alignment, right? The LLM, then the prompt, and also possibly the RAG documents, if you use them, must all use the same exact language. If you use slightly different terms, you are not going to be able to obtain optimized results, right? For example, if the definition of revenue in different data repositories is not the same, then when you are remediating data that contain the definition of revenue, you may get inconsistent results because revenue doesn't always mean the same thing in these different contexts, right? So the LLM must be trained on information that uses the same definitions as the prompt that you are using, the dataset that you are using, and if you are using RAG documents as well, that definition must match in all of these. Otherwise, you may still perform the operation, but there may be inconsistency in terms of what things mean. And just a quick mention to RAG or Retrieval Augmented Generation. We are going to have a module just on this, but it's imperative to explain a little bit what it is for those that may not be familiar, because it is a very good addition to generative AI itself. So what we usually do is we use external documents as data sources for queries. They provide additional context, additional information, and they help refine the answers, if you will. they refine the context for a specific LLM answer. RAG is good because it helps keep hallucinations in check, and it can also help track answers to specific documents, chapters, or others. Because if when you are creating what we call the embeddings, if you have metadata such as chapter 1, chapter 2, chapter 3, then when you generate an LLM answer, it's going to tell you, I picked this specific piece of information, or I fixed this value, taking into account this information on chapter number 3. So put simply, how does RAG work? Well, we pre-process documents and create what we call the embeddings, a vectorized representation of the text in those documents. Then, when the LLM is generating the answer, if RAG is integrated, then what happens is the LLM fetches the most appropriate embedding together with a query and uses it as part of the query. So you end up with an answer that is refined both by the prompt but also by the support documentation. And how can you use them? Well, for example, if you're trying to estimate locations or even transaction values for transactions that don't have a specific value, then you should provide support information such as, for example, bank statements or even activity from the specific merchant or the website that you may have where people perform the purchases. Then all of that information can be used to refine the estimation of values for those missing values. In other words, RAG works well when you have support information that helps you refine a specific answer for a specific purpose. Of course, you're going to have all sorts of sensitive questions here related to private information, confidential information, data sensitivity, safety of the models themselves, and data privacy and data security. But what you want to do is you want to use that support documentation to refine the LLM answers. That is what it is on a very simple level. So as we see, generative AI can be very powerful in helping us with data-related operations. But it's not all roses, right? There are a lot of possible drawbacks, and we have to mitigate these. We may have hallucinations, we may have increased computational intensity, we may have lack of transparency, or all of these at the same time. So it's very important to be aware of these before we start actually using these text generative models for data operations. We are now at the end of our fundamentals module, where we covered some basics of dealing with data, the data lifecycle, and generative AI before diving deeper into the more specific models with specific use cases. Let's take a moment just to recap the content of this module as well as some of the key takeaways. We are now at the end of this fundamentals module, where we covered some basics of data quality, the data lifecycle, and generative AI. To recap very quickly, what did we focus on in this module? Well, for example, the basics of what is data quality, the various dimensions, how is it measured, and how can we improve data quality with various operations, as well as the role of data management and data governance. Or, for example, the basics of the various stages of the data lifecycle, from the moment that they are created or ingested to the moment that they are destroyed, as well as how we can intervene with generative AI to increase data quality at various levels, and hopefully with automated pipelines. For example, automatically detecting new data, automatically detecting errors, fixing those errors, and outputting the corrected data set, for example. Or the basics of what is generative AI, namely text generative AI models such as LLMs, how they can help us increase data quality, but also things to keep in mind, and the role of RAG to help increase the accuracy of the generations. What are some key takeaways from this module? Well, data with high data quality are useful, and data with low data quality are not useful, and generative AI can help us increase data quality faster than human effort. Then, data quality exists according to specific dimensions. Is the value complete? Is it accurate? Is it consistent across various data sources? Is it timely? And so on. There is no general quality, only quality according to one specific dimension, and usually issues are issues according to each dimension. Then, data go through multiple stages in an organization, the data lifecycle. Generative AI can help us intervene at key stages. For example, when we're creating or ingesting the data and we want them to have high data quality to begin with, or when we are transforming them to a different schema, and a few other specific stages of the data lifecycle. We don't use generative AI in general, we use generative AI at specific stages for specific purposes. Then, generative AI generates new data, right? We mostly care about generative text models in specific, such as LLMs, for data-related operations. And like discriminative models that draw conclusions based on data, generative AI models generate new data based on inference. Then, generative AI has various limitations, right? Computational power, speed and scalability, hallucinations and wrong estimations, lack of transparency, and others. We can use generative AI, but we have to know exactly what are the benefits and what are the possible risks as well. And finally, RAG can be used together with LLMs to improve answers. We create embeddings from relevant documents, And then the LLM is going to fetch the most relevant information for an answer based on those documents. It can help keep hallucinations in check, as well as increase the accuracy of value estimation and other data-related operations. And with this, we close the fundamentals module with a quick recap and a summary of what is generative AI and what are data. We are now at our second module about data creation and ingestion, specifically at this stage. How can we use GenAI for data-related operations at this stage to automatically deal with incoming data by structuring those data, detecting the schema, and other related operations? Let's take a look at the content and lessons in this module. Welcome to this module on using generative AI for data-related tasks at the data creation or ingestion stage. In this module, we are going to focus on, for example, dealing with incoming datasets that may have issues in terms of missing values, biases, or unknown structures, and dealing with those using generative AI, or detecting issues, detecting patterns, or specific properties in datasets, either to structure a dataset or to remediate the low-quality data within that dataset, or making estimations of values, of relationships among variables, of formats, and other elements of data based on the properties of the dataset. In this module, we have 3 key lessons. The first is about synthetic data creation, that is, using generative AI to generate additional entries to rebalance the dataset, offsetting an underrepresented portion. For example, if we have a dataset that is missing a specific type of data, or data with specific ranges in terms of values, we can create synthetic data that are very similar to the rest of the dataset, but have those values of that specific range to rebalance the dataset. In other words, we can make up for underrepresented portions by generating additional data. Very straightforward. We use generative AI to estimate the real values for existing incomplete values. So we use the generative AI model to estimate the values in some way. And this may be for values that do not have a value, so incomplete entries, or for those that do have a value, but where that value doesn't make sense. And lesson number 3 is about schema extraction. That is, we use generative AI to automatically detect the data types, the value ranges, and other types of structure present in a dataset, which is very useful for when that dataset is unstructured or contains fields which are unstructured themselves. So as you see, this module is going to be all about using GenAI models for data operations when you are dealing with incoming data. Let's talk about synthetic data creation. This is a practice that is very important when you have a dataset, for example, that is unbalanced, and you need certain characteristics to be more represented because they are underrepresented. And GenAI can definitely help you with this. Let's take a look at how we would run through that process. Welcome to this lesson on synthetic data creation using generative AI. Let's start by defining what is synthetic data creation. Well, as the name says, the purpose is to create synthetic data or false data, if you will. But we use it to augment the dataset. Basically, we want to generate data to complement an underrepresented or a biased dataset to rebalance that dataset. Or in other words, if there is something that we don't have in the dataset, we create it from scratch. So what is the general process here? Well, usually we want to prepare the dataset to augment. We want to detect what is the problem with it, what type of augmentation does it need, and what specifically do we need to change. Then we select the model that is going to generate the new data. Because this is the general process, it's not with generative AI yet. So usually we'll have some sort of model that is able to create those data to rebalance that data set. Then we select the scope and criteria to apply. For example, do we want to augment underrepresented data? Do we want to create 10 entries with this type of value in this range, and so on? So basically, what guides the generation of those data? And then we actually generate the synthetic data. This step is very simple. And while this is the general process, where can generative AI help in specific for this use case? Well, for example, it can automatically identify either the underrepresented or the overrepresented portions of a dataset. Or in other words, it can automatically find out what is wrong with the dataset. And because Gen AI is so good at mastering context, it can also generate data that are similar to an existing dataset, but still introducing variety. It's very easy to feed a dataset to generative AI and to say, hey, generate 20 entries like these, but that have this specific field with these specific ranges, but still preserving the variety that exists in the other fields. It's very good at generating something that is simultaneously very similar and very different from the base dataset. GenAI is also very good at generating data which are extremely similar to the existing data. So it's very good for the task of generating synthetic data in the first place. It's very good at taking something and continuing it. And possibly more than anything else for this use case, generative AI is good at generating these additional data in a fast and scalable manner, because doing it with another type of model or with human effort would take time. But with generative AI, you can simply copy-paste the dataset and say, hey, generate 10 more entries like these, and possibly give it additional criteria or instructions, and in a couple of seconds, depending on the computational power of your system, you will have the answer. So when we are generating synthetic data with generative AI, what is some prompting that we could do here? Well, we see something like, hey, generate a dataset with a similar range of ages and locations, for example, for transactions or for customers, but that has diversity in terms of transaction amounts. Or for example, please create additional patient profiles based on this dataset, preserving the age in the diagnosis type value distributions that exist in this dataset. In other words, generate more false patients, if you will, but with similar ages and similar conditions at similar stages. And what are some best practices when we are using generative AI to generate synthetic data? Well, one is that we have to define the constraints clearly. That is, what value ranges do we need to preserve and which values do we want to vary? This is very important because otherwise generative AI is just going to generate random data. You have to be very specific about what is supposed to change and what is supposed to stay the same. And in many cases, you are only going to know this after performing statistical analysis. You have to know what is wrong with the dataset so that you can then guide the generation. Doing this without preparation is a recipe for disaster, or at least for randomness. Then, it's also important to verify the value distributions for the generated data. That is, LLMs usually generate consistent data, but it's still important to verify. There may be a hallucination, or maybe it doesn't understand what is evenly distributed, or maybe you use different terminology and it doesn't understand it that well. So just because you said generate 20 customers with ages in this range, it doesn't mean that it's actually going to do it. It's probably going to do it, but still, you should run some sort of statistical analysis just to make sure that the dataset really is balanced after this change. And naturally, as for many other use cases, there are risks and limitations to using generative AI for this purpose. These include, for example, bias. That is, while the goal of synthetic data generation is to reduce bias, do remember that LLMs may actually have biases themselves. And these can be biases of the same type or different types. In other words, you may be trying to balance the age distribution when generating false customers, if you will. But the problem is it may introduce biases now in terms of the location, because you didn't give it any direction in terms of what to do for the values of the location property. So now there's bias in location. And it may be the same sort of bias, preserving biases that exist for new fields, or it may introduce completely new types of biases. For example, maybe it generates 20 entries and all 20 entries have the same location. You didn't tell the LLM to do that, but you also didn't tell it not to do it, right? And again, this is why it's so important to specifically tell it what to change and what not to change in terms of the fields. Then, there may be other correlations or patterns. Some of these we may not even see, or we may not have them explicitly stated. So, if we are just looking at certain dimensions of the data and ignoring other dimensions, we may not notice that the LLM may generate synthetic data with other correlations that go unnoticed. In our example, if we do have a customer field and we are running statistical analysis on a lot of fields, but we don't run it on the location property, we have no idea what is going on with the location. So if we generate 20 additional entries, but we don't do any type of analysis for the location entry, we have no idea of those 20 new locations. Are they going to be similar? Are they biased? Do they all have the same value? And so on. The only way to know what may be wrong is to analyze that dataset for biases according to all possible fields, because you never know what the LLM is going to generate. It's probably going to be something that is fine, but probably doesn't cut it in a lot of situations. Okay, so let's cover a quick example, starting with synthetic data creation, how to actually do this. So I have installed here Olama, which is a wrapper for multiple types of open source LLMs. And what I'm going to do is to use DeepSeek in this case, the open source version, not the commercial version that sends the data to ByteDance. And what we're going to do is we're going to generate some synthetic data using this. Okay, so I have organized some folders here with the different purposes that we're going to have. And what I'm essentially going to do is we have a data set here. I put it as text format because I didn't want to deal with all of the complexities of using CSV or some sort of relational format. So what I decided to do is just copy and paste some of these as TXT files, because you may have to deal with them. You may have to do some conversions or to deal with data in multiple formats. But at the end of the day, I just want this to be in an easy format so that we can focus on the LLM in specific. And what I'm going to do here is I know that we can interact with the LLM itself because I can do, for example, Olamaran, I think it's DeepSeek R1, if I'm not mistaken. I think I have the 7B version locally, and we can send a message to it and say, hi, what is the best car or something like that. And it'll answer, right? But what I want to do is I want to run it with the prompt as the text file because we want to have that flexibility, right? As you see, we have a prompt here, right? But maybe we're not going to be able to copy and paste this gigantic table into the prompt. So it's outputting a lot of information about cars and supercars, I guess. But what I want to do is I just want to show you that we have this local LLM running and we are going to use it. So what I want to do essentially is just cd to this folder, and I'm going to copy and paste the prompt in this prompt text file so that it's flexible, right? So in this case, it opens Sublime Text in the other monitor, but here we have the information. And we're going to do something like, hi DeepSeek, I would like to generate 10 new records that are varied and that maintain the same distribution as these ones. What we could even do here is, because we have a big focus on New York City, I'm not using any data profiling tool, but you can see that there's, a big concentration of New York City here. We can say that maintain the same age distribution as the current ones, but that have variation in terms of geography, okay? So now we're going to save this prompt, maybe say here is the data set. And now pretty much we just run DeepSeek and we pass on the prompt and we see what it says. Okay. You can notice here, we're going to touch on this when we talk about the scripts and the pipelines, but right now it's showing it's thinking too, right? So this part is just the thinking, and then this part is the output. We can already start thinking about prompt engineering here because we see that this is divided with pipes and it doesn't look that good. But what we can do is naturally adjust our prompt and say something like, here is the data set, please output the data set as CSV and nothing else, okay? And if we repeat the process, so it is going to show our thinking. You can see that it's analyzing the age distribution, okay? And it's even doing some sort of statistical analysis already and thinking, hey, this is the age range that we want to have. Let's maintain that age range, right? You can see that it's actually going a little bit too deep on the ages, but we'll take a quick look at this to make sure that it really does make sense, right? So the average age is 37 here. Is it 37 though? So 34, 29, 41, 36, 52. It seems to check out at first glance, right? Okay. We can even see that it's doing a lot of back and forth in its thinking, right? Just pick randomly. You can see that it's hesitating a lot in terms of, what it's deciding to do. Okay, so here are the 10 new synthetic data entries, right? It didn't do exactly what we wanted. I mean, it did output the CSV, but it still says here are the 10 new synthetic entries. What I want to try to do here is I want to try to limit the answer to just the literal table so that we can feed this to some sort of process in the future, or so that we can use this. Because right now, we cannot parse this, right? Because we have a line of text, and then the entries, and then another line of text. So what we can do is go back to our prompt and change it again, right? Please output this as CSV, nothing else. No text, just the table itself. No need for numbers or any sort of bullet point. Just output the actual data set ready to copy, paste in a script or application. And let's see if this takes care of it. So we're going to run it again. And depending on the model that you have, the thinking may, be a lot or a little. to be honest, I have not compared this with, for example, with the Llama model or others. I'm just using DeepSeek, but we can try another model later and see if the thought process is different. In this case, the thought process was actually a lot more compact, right? Because if you think about it, right, there's just 5 or 6 paragraphs. But you can see now that the output is this one, right? So out of curiosity, let me go here and let me open this text file and see, do the new synthetic data kind of gel with the current ones? And actually, yes, it seems so. 34, 29, 41. So what it did was, it seems like it's literally copy pasting the age distribution, 52, 27, 39. Yeah, so it's literally copy pasting the age distribution instead of randomizing the ages, which may not be the best practice here, but we can modify the prompt again and say to introduce a little bit of variation. But what we focused on in specific with this prompt was we said, hey, we want the same exact age distribution, but we do want variation in terms of geography, right? Dallas, Chicago, Houston, San Francisco. I mean, we didn't even specify in terms of the geography either, right? So is it in the US? Is it in Europe as well? Is it around the world? But based on the prompt that we have, these are acceptable results. So let me go back to this now. I'm not going to save it. And let me say, okay, maintain the same age distribution. So this may be a problem with the prompt as well. Maybe it assumed that it wasn't just the age distribution, but maintain the actual ages. Okay, so have variation in terms of geography. Ages should not be exactly the same, but appropriate. And there's other factors here, such as, for example, if you notice, the new database, I didn't put it here, but the new output database have another person called literally John Smith, which would be a repeat here. So we can also have some variation in terms of the names or in terms of the specific ethnicities for the names or something else, right? You may also want to introduce some diversity here, but it depends on you, right? But at the end of the day, considering what we asked in specific, these are acceptable results, right? So now we said ages should not be exactly the same, but appropriate, not appropriate, a bit similar, okay? Just to have a little bit more variation. And now let's see what it does, right? So let's feed the same prompt again. Let's see how much it's going to think at the end of the day. So you can see that we're introducing a little bit of entropy because the previous solution was pretty simple, right? Just maintain the ages and it's simple to generate and it's easy. Here, as we can see, we already have different ages and we have different cities as well, right? So if we go to our existing data set, okay, we can see that this is acceptable, right? We have different names, we have approximate ages, but not exactly the same. So this is how you would generate it, right? So now let's do the following, okay? Let's make this example a little bit more complex. So let's do this. Please also add a new column called similarity score, right? And similarity score, what it's essentially going to do, it's going to tell us from 0 to 100% how similar the new entry is to the existing entries. Please also add a new column called data source that tells us whether the data are from the original data set or synthetic data. When we can also include the original data set in the response, right? So this is an option because you may want to include the original data set as well so that you can see the whole data set with the new entries or just generate the new entries. It depends, right? Because LLMs have a tendency to change the original data if you try to get the original data back in the response, but you could use it just as a reference to get the whole data set and see what is different. Okay, so let's run this variation. It's showing us the thinking again, which is interesting. You can see that sometimes the thought process is a little bit different, right? In certain cases, it just thinks about locations in general. And in other cases, it takes the current locations, it does the distribution of those, and then it inserts new ones, right? So the interesting thing here is, okay, we copy paste this here. We can see these are the new data, right? And we can see that it did maintain the current entries. We did have a little bit of loss here in terms of the formats, because you can notice that the double quotes were removed from the electronics or books, right? That's something that can happen. Maybe we can literally regenerate the answer, but at the end of the day, right, you have the original entries here, but you can already see a little bit of hallucinations here, right? Because, for example, this Jennifer Williams, 27 years old, Los Angeles, this is not a synthetic entry. This is an original entry, right? So again, this is one of those things where you may not want the LLM to include the original data because it may change the original data. But if you just consider the new entries, yes, they all say 70% synthetic, and we could run the prompt again and ask it to consider the double quotes to escape this field and to make sure that these are considered just one field. But at the end of the day, it gets the job done, right? I don't know if it would be better if we have a specific LLM that is fine-tuned on specific data operations as well, but you can see how the process goes in general, right? So as we see, GenAI can be used to create synthetic data to help you rebalance a dataset that may have underrepresented characteristics or underrepresented values in specific. It is important, however, to guide it properly so that it really creates the data that you want it to create. Let's talk about completion of incomplete values, which is one of the most typical use cases in terms of remediation, if you will. Basically, we have a data set that does not have values for a specific field, and we need to fill those values in some way. And we are going to use GenAI to help us with this. Let's take a look at how. Welcome to this lesson on completing incomplete values in datasets using generative AI. To begin with, what is completing incomplete values? Well, for remediation purposes, we may have to fix a dataset by either replacing or removing incomplete entries in that dataset, because those entries may compromise the quality of the dataset. So we have to handle them in some way. And what is the general process, even without considering generative AI, just in general? Well, first, we identify the incomplete values, such as by using data profiling with statistical methods of some sort, such as knowing, for example, what is the fluctuation in values for this specific field, what are the outliers, and what are values that just don't make sense. Then we want to identify data sources that are going to help us to estimate the real values, such as, for example, values of other features in the same entries or external data. That is, in order to estimate a value, we must have information, right? For example, if you are missing the transaction value for a purchase, how are you going to estimate that transaction value? You can't do it out of nowhere. Maybe you have a customer that is associated and you have the average transaction value for that customer. Maybe you have a location and you know the average transaction value for a location, and so on. But either way, you must have some sort of additional information source or sources that give you context for that estimation. Then we use some sort of model to estimate these values, such as, for example, a regression model based on certain predictor variables, right? Before considering generative AI, these are the types of models that were usually used, right? You have some sort of model that can take in information and estimate a value based on that to draw a conclusion. Usually, it's going to be a regression model because you want to estimate a specific value, but it may depend on the type of content, whether it's structured or not, and so on. And with this, we generate those values based on that model. So how can generative AI help in this use case? First, it can recognize patterns. That is, generative AI doesn't need a statistical model or a predictive model to notice what is the probable value of something. It can just take in the context and estimate the values based on that context. So it can do it in an intuitive manner, if you will, based on the correlations of words and text patterns. And generative AI also has the advantage of being data agnostic. That is, it can take data in various formats, structured or not even structured, and it can use them all as the context for predictions, which makes it a very flexible type of model. You can generate values for numerical fields, enumeration fields, string fields. As long as you have the proper context that allows the model to estimate something, it's going to be able to estimate it. Whether it's going to be with a high level of accuracy or not, that's another question. But the more that you have context and backup information, and the more that you provide information about how to make that estimation and what you want, the higher the chances of obtaining good results. What are some prompting examples for completing incomplete values with generative AI? You could say, for example, hey, given this specific data set and this additional information source, such as documentation, please predict the missing values for this specific field that says transaction value. And you can also add additional things to the prompt, such as saying, hey, please add a confidence level as a new field or a justification for every single entry as a new field and add that to the dataset. Or saying, hey, given this dataset, please predict the values for the missing diagnosis type based on the entries that are the most similar to the ones with missing values. That's another approach, right? Instead of just using backup information, you can say, hey, based on the existing entries that are the most similar to this one, please estimate the value for this entry. And it's going to use as the context the rest of the entries in that dataset. What are some best practices when we are trying to achieve this? Well, you have to specify the patterns. That's a best practice. For example, if you have transaction values, maybe the customer names don't matter. So the correlations between the customer names and the transaction values are irrelevant. So what you want to do at the end of the day is you want to tell the generative AI model what are the correlations or the values that are relevant and the ones that are not relevant. It can already do this to an extent, but it's better if you explicitly state that. For example, saying, please estimate the values for these transactions, take into account location, product type, and so on, and don't take into account the customer name, the customer ID, and so on. Sometimes these things seem obvious, but there may be random correlations in the data. And if you don't tell the model to explicitly not use them, it's going to use them. Then another practice, which is a good practice not just when using generative AI, but in general, is to avoid making predictions with scarce data. Look, if you only have one or two other predictor variables or no additional data, then maybe you shouldn't be making predictions, right? As we said, the more context and the more backup information that you have to make an estimation, the better. But this also means that if you don't have backup information or context, then you can't make a good prediction. And in these cases, it's better to admit that you cannot make a prediction and leave this task for later instead of trying to make a prediction that has a random value and then you get a false sense of security because you have an estimation, but that estimation wasn't trustworthy at all, right? So in certain cases, when you don't have good enough information, it's better to simply not make a prediction. And as usual, we also have risks and limitations when using generative AI to complete incomplete values in datasets. One of these is that there is the potential for inaccurate computations, for all of the reasons that we've stated here, right? So if generative AI makes predictions from scarce data or from irrelevant variables or from errors that were not fixed in the dataset, then the predictions can be wrong or inconsistent. This is one of those cases where the maxim of garbage in, garbage out applies, right? Because we are making a prediction or a regression based on specific variables, then what happens is the lower the quality of those variables or that information, then the lower the quality of the output as well. As simple as that. So you need to vet those backup information sources or the other variables that you are taking into account very carefully because you are generating new data based on those. And also, another possible limitation is that the predictions are general and not granular. This is because generative AI cannot work with mathematical values to extract extremely precise values. It works mostly for general predictions or for intuitive predictions. So it is faster than a statistical regression module, sure. But in a lot of the cases, maybe the results would be better with a statistical model, right? And another thing is that you also don't have transparency on the justification. If you're using a regression model, then you know what is the role of the predictor variables in the final output. But if you're using a Gen AI model, maybe it provides a justification, and maybe it's not even a good one because it's based on the associations of text patterns and text tokens that exist in other sources. And that may not be good enough to have a quality estimation. So this time, our example is going to be completing incomplete values, which usually is the kind of canonical, usual example that you think of when you think of data remediation, right? How to fill in data which are missing. And what I've prepared this time is a simple data set that has transactions, right? So it does have number of transactions with the description, amount, all of the usual elements, if you will, but the category doesn't exist in all of these transactions, right? So you can see that it's not filled in some of these. And what we're going to do is we're going to ask the LLM to fill in the missing categories based on the description of the transaction, right? Which should not be too complicated, right? So we're going to structure our prompt and use this in the same exact format as the previous example, right? So, hi DeepSeek, please fill in the missing categories based on the description of these transactions. Please return only the data set in your response, nothing else, so that I can easily copy paste it. And then we have data set here, okay? So let's run this and see whether we get a good result or not, okay? So getting at the prompt, again, it's thinking, okay, data set of transactions. And this is really interesting because in certain cases, when you have errors or something is not in the right format, you can go through the thought process of the LLM and see where is it going wrong, right? What is it understanding in a different way or not in the correct manner? Okay, so let's take this and just copy paste it here and see Okay, what are the changes here? Okay, so the second one didn't have a category, has been filled as groceries. Well, coffee and sandwich. I don't know if this would be groceries or meals. It depends on the taxonomy that we're using too, right? So because we didn't specify the categories, then maybe the results are not going to be optimal. What is another one? Monthly subscription for a streaming service. Entertainment. Yes. Again, it depends on the taxonomy. Are we focusing on what is the category? Whether it's, for example, leisure, whether it's electronics, whether it's essential expenses, or are we focusing on, for example, is it digital versus is it physical? Is it a one-time purchase versus a recurring subscription? So when we're asking it to fill the category, we also need to define what are the available categories. So this does seem acceptable, but it depends on what our goals should be. Here, large appliance repair service, it filled it as healthcare. Okay, so this one is a little bit iffy. What we can also do is we can ask it to provide a justification later so that we can see the rationale behind some of these. Maybe it's assuming, for example, that it's an appliance that has to do with health. I don't know. I'm trying to justify the LLM's results, but honestly, I don't know in this specific case. So now what we're going to do is we're going to have a little bit more of an advanced example, and this is exactly what we're going to do, okay? Please add a new column called confidence score, indicating how confident you are in your predictions, and also rationale with a quick one-liner on why you failed that specific category, okay? So everything else is exactly the same. We're just asking for these two short additional fields, okay? And how is it going to go? By the way, that appliance transaction that got the wrong category, if you want to consider it wrong, maybe we could have gone to the rationale here and thought about what happened, right? So large appliance. This falls under healthcare because it involves medical or dental services. I wouldn't necessarily agree with this, but we didn't specify, right? Maybe we can talk about what it defaults to in the different categories, right? Okay, so now we have a little bit of an error here again, which is it's, again, outputting the data sets separated with pipes, what we don't want, right? So let's open the prompt and say something like, please output the table as CSV without any other sort of delimiter or effect. I did not even look at the actual output. We can take a look at the output, but I just wanted to make sure that we got the right format, because this is in preparation for module number 5 when we're going to be using this in pipelines. And if we're using this in a pipeline, if we can't parse the output immediately because there's more text or it's in a different format, then the whole script halts to a grind, right? So you can see the rationale here. And this is interesting because I'm assuming that these are going to go into the individual justifications of the final data set. Okay. So we can see naturally that, for example, the ones that already have the category, we are not attributing the numbers, right? But for example, this one that is missing the category, it didn't add the category, which is a little bit weird, right? Same here. It's not adding these things. So for each transaction where a category is missing, I'll infer based on the available information. But the problem is it seems like it didn't infer those, which is a little bit weird. So I'm wondering if there's some sort of issue because the confidence score and rationale are going in the middle of the existing fields instead of being the last field. Okay, so we're going to modify the prompt again. Again, your mileage may vary. Maybe you have a specific LLM which is fine-tuned on this, or maybe you have other ways of making this more effective. But for now, we're going to work with what we've got, right? Just for illustration purposes. So these two columns should be the last columns. Always fill the category when it's missing in all cases. This is a little bit redundant, but sometimes you just have to push and insist more on something until the LLM does it, because it's a probabilistic model, right? For example, if it does have somewhat of a tendency to fill the values, if you just ask it in a more insistent manner to fill those values, you can kind of brute force it until it does fill the values in all locations. And again, depending on your processing power and computing power, maybe you can repeat this until you get the result that you want. If you're using this in a pipeline, then it's not that easy. But if you're using this for a one-off repair, maybe you can just repeat it 3 times or 4 times until you get the exact result that is acceptable for you. And then it's on to the next operation. Okay, so here we do have the confidence score in the rationale, but we don't have the category, which is weird. Okay, so it's exactly the same thing that was happening previously, but it's not filling the category itself. It's showing us the thought process, but it's not filling the category. So we're going to ask it to do exactly that, right? Always fill the category when it's missing in all cases. Besides the confidence score and justification, always fill the category. I'm just insisting at this point, hoping that it's going to do it, because probabilistically it should, right? What may also happen here is that in certain cases, the attention span of the LLM is not enough for you to do all of these things at once. So you may end up with a situation where you literally are not able to do all of these things at once. Maybe you can fill the value and get the confidence score, but not the rationale. Maybe you can fill the value and get the rationale, but not the confidence score. So if everything else fails, we'll just fill the category and the confidence level, and we'll leave the rationale behind. Maybe there's also the possibility that including the rationale is making the LLM focus on the thought process and not on the results, but we'll tackle that later. So we can actually see that it's acceptable now, right? Food and dining. Let me look at the appliance one. Where is the appliance? Appliances. Okay, so the confidence score is 2. Is this the confidence score? Okay, so you can see that it's a little bit shaky in terms of the confidence score. It's not from 0 to 100 anymore. It's 1 or 2 or 1. So we can ignore the confidence score here, or we could even repeat this without having the confidence score and just with the rationale. To be honest, if I had to pick one of the two, I would include the category and the confidence score, right? Even if you don't have the justification. And again, this may also depend on the version of the LLM that you're using, because I'm using, I think it's the 7 billion parameter version of DeepSeek. If you have the computing power to use the 7TB version, naturally, then that's going to be completely different in terms of the intelligence of the model or the sophistication. So this is also an important lesson in terms of working with the model that you have. What are the limitations of that specific model and how can we overcome them? And in a lot of cases with the attention mechanism, it's just about requesting less things at the same time, and then it should work out. So as we see, we can use GenAI to complete values which may be incomplete, but we do have to be careful because we cannot complete those values based on scarce data because the predictions are not going to be accurate, and we have to be very specific about how those values should be completed because it's not a generic process and we need specific criteria or guidelines. Let's talk about extracting schemas from datasets using GenAI. That is, when we have incoming datasets where we don't know the schema or the data formats or the specific value ranges and others, we can use GenAI to capture the schema or at least to kind of obtain an estimate of what are the formats, the usual value ranges, and more. Let's take a look at how we would do this. Welcome to this lesson on schema extraction, where we are going to cover how to use generative AI to automatically obtain the structure or the schema of incoming data that may be structured or not at all. What is schema extraction to begin with? Well, put simply, when we are taking incoming data that don't have a specific schema or description of the structures, the fields, and so on, we have to detect that structure. We have to find some way to derive the schema or the structure of that dataset based on the contents. And generative AI definitely helps with this. But before generative AI, what is the general process for this? Well, first, we want to inspect the dataset's columns or features or data types. And do notice here that the datasets may have a lot of different content types. They may be structured or not. They may be relational or not. So there's a lot of variety that can occur here. But we have to inspect the dataset in some way and start to break it apart to think, hey, these are the columns, these are the entries, and so on. Then we want to detect patterns that allow us to infer the data formats, right? Are they numbers? Are they dates? Are they codes for enumerations, and so on? Some of them are very basic, right? For example, if you have a column that has the name price and there's only numbers in there, then it's probably a price, right? But it may not be named price, and you just have a field with various numbers. And are those numbers actually currency, or they may be in another format? So some of these fields may be very intuitive and others maybe not at all. Or you may have codes which in a specific enumeration are mapped to a specific meaning. But if you don't have that enumeration or that translation map, then you may have no idea what those codes actually mean. So some of these fields may be very easy to interpret, while others may be very difficult. And then what we want to do is generate the metadata, right? Because the description of that schema and the fields is metadata. So this may include the fields, the formats, the data types, the ranges, and so on. We want to document the data set in terms of its schema and its structure at the end of the day. It's a good description of what we are doing. And how can generative AI help here? Well, in this case, it helps, for example, by detecting the structure easily and quickly, right? Generative AI can easily take a snapshot of a dataset structure without needing to run statistical methods or analyzing individual columns or features or entries. Chances are, if you copy-paste the dataset into a text generative AI model and ask it to derive the structure, it's going to make some very accurate guesses. Why? Because of what it has seen before in the training data, the relationships between certain variables, and so on. It's very good at making intuitive guesses of that structure and doing it relatively quickly. And generative AI is also especially good at detecting common formats. Why? Because most LLMs have knowledge of the common date formats, the common number formats, and more. So they can not only identify the data formats in a specific dataset, but even the specific subformats within these, right? Currencies, data formats, scientific notation for numbers, and so on. Why? Because again, they have seen these formats in all sorts of things, right? Financial transaction datasets, research papers, annual reports by companies. So even if you have specific fields that have very specific patterns, chances are the LLM has seen it before and can attribute the correct range or the correct format to a specific field. How would you prompt a generative AI model for schema extraction? Well, you could say something like, please analyze this specific dataset and identify the schema, including the data types and the value ranges for each column present. Or, please generate a summary of the fields in the specific dataset, including the potential primary keys and the foreign key references, right? So we can go deep and ask it to take into account specific fields or to go deeper on something specific, or we can just ask it to attribute the schema and the formats in general. It's up to you and what you want to do, including what you are going to do afterwards, right? Are you going to flag the schema for review by a person manually, or are you going to accept this result and run it automatically in a pipeline, which is not recommended, but some people can do it. And again, naturally, it also depends on how complex the data set is, right? If you have data sets which are unstructured, but you already know that there's going to be probably two columns, one with text and another one with integer numbers, then you can do it automatically. But if it's a very complex data set, you don't want to run that risk. So it depends heavily on your use case and what you want to do after this step. And when doing this with generative AI, what are some best practices here? Well, one is specifying the level of detail again, right? Do we want to just identify the data types? Or do we also want a description of these, right? Do we want to estimate the value ranges for each two? Or do we just want the format in general, right? We can do it all at once, or we can, if we have enough computational power in an LLM with a big enough context window, but do take into account that in certain cases, it's better to do certain trade-offs. Maybe you do two passes, for example, where the first pass is just detecting the formats, and the second pass is detecting the specific value ranges, right? So it depends on what you want to do. And another good practice is ensuring that the dataset is representative, right? Because biases may exist, outliers may exist, and we may have other statistical patterns that may skew the data, right? So you want to consider cleaning that dataset first, or using a sub-dataset that is a representative sample. Or you can even combine this with the generative AI use case that you have, right? You can ask the same LLM to first clean a dataset and remove the bias and then detect the structure. Because in certain cases, if you're calculating value ranges, for example, then the existence of biases or outliers can definitely skew those ranges and give you incorrect information about a schema. Or you can literally have data which are not formatted properly and that don't belong in the dataset and that literally change the format of the dataset that is detected because they should not be there in the first place. And as usual, we do have some risks and limitations when we are using generative AI to extract the schema or the structure from a dataset. One of these is that generative AI can be overwhelmed, right? If the dataset is huge, if the dataset has complex relationships among variables, if the value ranges are very big, and if the columns have ambiguous names or no names, then the LLM can make wrong predictions. Because think of it this way. The LLM makes an intuitive prediction. The more that you try to do at once, the less that its intuition works in a way, right? An LLM works by text pattern recognition, right? So the more patterns that you throw at it at once, the less that it's going to be able to keep up, right? So in many cases, you want to consider using a subset that is smaller to derive that format, or you may want to consider cleaning up the dataset first, or even already detecting the value ranges and then feeding those value ranges as well for the LLM to detect the final schema, if you will. There's a lot that you can do here to make life easier for the LLM so that the LLM makes life easier for you afterwards. And another risk is that generative AI doesn't work very well for complex or nested structures. This is a very particular type of risk, unlike the other generic risks, if you will. But it is true, right? So for example, if we have a nested JSON document with hundreds of fields, the Gen AI model can't easily analyze these versus a more traditional structure. Why? Because it reads it vertical, right? And it has to read the first entry with all of its details before stepping to the next entry with all of its details. It's almost like if you are reading a structure like JSON, you are starting bottom up. And if you have a structure such as a table, you are starting top down. And if you are doing it bottom up, then the Gen AI loses its major advantage, which is the capability to generalize and to take the top down view of something, right? So for certain structures such as JSON, maybe you can consider chopping off some of the fields to make it easier to process all at once, or using an LLM with a bigger context window, but results may vary here. So in this lesson, we're going to extract the schema from a dataset. So what I prepared here is a simple dataset of various products, a product catalog, if you will, but the columns are unlabeled. So what we're going to do in a very simple manner is take this dataset and then ask the LLM, try and calculate the schema and output the schema, or the dataset together with the schema. Okay, so we open up our trusted prompt here. I'm starting to think that across these operations, maybe there are certain guidelines that we want to preserve because they're always the same. Something like, for example, please output only the dataset with no other text, something like that, right? So let's say, hey DeepSeek, please calculate the schema for this unlabeled dataset, right? And for now, I'm just going to keep it simple and see how it goes and refine the prompt as we obtain certain results, right? Okay, running this version. And by the way, because this is a dummy data set, maybe I don't have a way of validating whether these actually are true or not, right? Again, okay, another thing that we want to always have in the prompt is the limiters, right? I can already see that this DeepSeek LLM does not like CSV at all. So please output only the dataset with no other text. Please output it in a CSV format so that I can easily copy paste it or use it in a script. Maybe I didn't even need to give such a justification. Why do I want to use the CSV? But maybe it's going to associate, data that are usually used by applications or by programmatic means usually have a very specific format. So it's going to remember to output this in a very specific format. So it's a little bit of prompt engineering here. Okay, so we change the prompt. Let's try again and see where it goes this time. Okay. And I'll take a look at the fields and check whether those make sense or not after we actually generate the answer. Okay. So first of all, it's saying here is the data set. I don't want it to say this. I only want the actual data set, but we'll focus on that later. Okay, so if we take a look at this, right, does this sound realistic, right? So product ID, possibly. The first column is always the ID. Product name, absolutely. It's a name. This is probably a price. Yes. Stock. So this is an integer value that is above 0. It does make sense that it could be the stock, right? Then category, I don't know why category is in all caps. Maybe the categories are important, but okay. Furniture, electronics, appliances. Yes, it's definitely the category because we can see these keywords here, right? Lighting, etc. Color, yes, because it's a set of colors. The Y or the N, honestly, I don't think that it is whether we have stock or not. So first of all, I see that there's a little bit of a typo here, I think, because this Y, comma, N, this is supposed to be the same thing, right? Is it a yes or no? But because we have a comma here, then it's introducing this as 2 columns instead of 1, because this is a CSV, right? Which is what we don't want. And I don't think that this is whether the stock is available or not, because it doesn't make sense to me, right? I don't think that you would use this because we do have stock numbers, which are values that are above 0. So it doesn't make sense to me that this would be stock, yes or no. Maybe this could be something like, is there stock in a different unit or whatever it is? Is there stock in a different warehouse or in the central fulfillment center or whatever it is? That could be interesting. But if we have numbers of stock which are above 0, then definitely this is not whether do we have stock, yes or no. but that's just a minor gripe that I have with this. And then the date, then the size could be the size, but this is the size in what type of units, right? I'm already getting into the metadata and the definitions, but we'll talk about that later. And the final one could be the SKU, right? So this sounds reasonable. Now, what I just want to do is I want to make sure, first, that I don't include this in the prompt. I could include these as kind of global instructions for the future as well, which is when outputting column names, please ensure that no names have commas in them as not to disturb the CSV format. And I'm going to make it really strong, this prompt part that says only the data set, no other text. Please output it. I can easily copy paste. Do not output anything besides the data set as not to prevent parsing of the response. So now it's worded in a pretty strong manner that I don't want this to output anything except the data set itself. Let's see how it works, okay? In this time, we have, for example, the size or the indicator, values like Y indicating yes or no. So could this be a size? Could it be something else? Possibly. But it seems like it's merging these two columns as well, right? Because the size is one thing. And what is the Y or N, right? We have color, we have size indicator, purchase date. Okay, so I don't think it's a purchase date because this is a product catalog, but we can go back and forth, right? We could add to the prompt something like, hey, please do not include anything that would be related to a specific transaction since this is a product catalog. But I'm getting ahead of myself. We already have what we want, which is that it just outputs the data set with nothing else. And what we could do in this case is we could, have somebody from the data management team or whatever is the appropriate team validate and vet this as the output instead of just trusting this, right? And it could also be a situation where we do the first pass and we agree that most of the fields are correctly detected, but there's one that is still not correctly detected. For example, this size indicator. I have no idea what this would be. But what we could do is we could send this back to somebody that deals with these products and ask, hey, we have identified most of the fields with confidence, but we don't know what this specific one is about. So can you give a specific example of what is this 4.2 for this office chair? Can you give us some more context, right? Again, it raises another question, which is how much information do you have on that schema? If you have no information, which is the worst case scenario that we are doing, then it's going to be hard. But it may be the case where you do have somebody that you can call and ask, hey, do these always make sense? Is this column correctly identified? And so on. But this is how you would do it, right? You feed the data, you say, this is what we want to detect, and this is the format as usual. So as we see, we can use GenAI to automatically detect the schema of a specific incoming dataset or datasets. But we do need to be careful about certain things, such as, for example, if you are estimating the value ranges, make sure that the dataset that you are using really is representative, because otherwise the ranges are not going to make sense. We are now at the end of the data creation and ingestion module about using GenAI for data-related operations when we are acquiring those data or creating those data. Let's take a moment, as usual, to recap the content of this module and some key takeaways. We are now at the end of this module on using generative AI for data-related operations at the data creation and ingestion stage, where we focused on how to use generative AI to help improve data quality when you are creating or acquiring those data. What did we focus on throughout this module? Well, we focused on dealing with incoming datasets that may have issues in terms of missing values, biases, or unknown structures. For example, we are acquiring or creating the data, but we don't know something about it, or something about it is known and is wrong. Or, for example, detecting issues, detecting patterns, or just detecting properties in datasets, either for the purpose of structuring them or remediating data quality issues, or making an estimation of a value, a relationship among variables, a format, or other elements of data based on the dataset properties. What key takeaways do we have from this module? Well, we can generate synthetic data to offset underrepresented portions of datasets, but remember, we have to be clear about the constraints and about what value ranges to preserve and which ones to vary, because otherwise you may end up with new data that are random. You have to know exactly what is going to be the same and what is going to be different. Or, for example, we can estimate the missing values, but generative AI must have enough data to extrapolate from. Remember, garbage in, garbage out. if it derives the values from context, then the quality of that context and that information is everything. And it must also know what specifically to take into account and what not to take into account. What should you use to estimate this value and what should you not use and say that explicitly to an LLM? Or for example, we can detect the structure and the formats in existing datasets, but this can't be done for certain structures such as JSON or nested structures, or it can be done easily, at least, and we should not overwhelm the LLM by asking it to do a lot of things at once with complex relationships in huge datasets. So the more that we can make life easy for the LLM, the easier that it's going to be for it to calculate that schema, or to estimate that schema, I should say, because it's always an estimation. And with this, we close this module on data creation and ingestion about using GenAI for data operations when we are capturing or creating data. Welcome to this module on using GenAI for data remediation in specific, which is the more standard use case, if you will, in terms of data remediation. How to cleanse and standardize data, how to augment and annotate data, how to do data profiling, find anomalies, perform statistical analysis, and actually fix those data. Let's take a look at the main topics and lessons in this module. Welcome to this module on GenAI data remediation, where we are going to focus on how to use GenAI for data-related operations, but specifically at the remediation stage, when we are improving the quality of a given dataset. So, in this module, what is going to be our major focus? Well, for example, automatically identifying biases or statistical imbalances or erroneous values or other sources of issues in data by leveraging GenAI. Or, for example, how to actually deal with datasets that may have biases, incorrect values, overrepresented or underrepresented sectors, or other imbalances, and actively addressing these. Or in other words, using GenAI to actually fix data, if you will, remedying data. Or, for example, how to add more information to increase or refine those entries by adding additional information to these. And GenAI is very good at summarizing and taking information from context or additional sources to embed in data fields. How many lessons are we going to have in this module? Well, we are going to have 4 in specific. For example, lesson number 1 is about cleaning and standardization. That is, how to use generative AI to actually identify and address erroneous entries in datasets. Then, lesson number 2 about data augmentation. That is, how to use GenAI to enrich or augment entries with additional data, which can then be leveraged for data science or other uses. Basically, data may already have high quality, but we want to add additional information, which can be useful later. Then, lesson number 3 is about statistical analysis and anomaly detection, or in other words, using GenAI to do kind of a preliminary data profiling, if you will, statistical analysis, and finding the biases or the problems that result from that analysis. Then, we're going to have lesson number 4 about data debiasing, smoothing, and noise reduction, which is about how to use GenAI to correct any biases or value imbalances in data themselves. Not so much about remediation, but about correcting in terms of sampling what are areas that are overrepresented or underrepresented and how to balance that. So as you see, this module is all going to be about using GenAI for data-related operations in terms of hard remediation, if you will. Let's talk about using generative AI for cleansing and standardization, which are 2 operations which are very common in terms of data management. Essentially, you may want to remove noise, you may want to standardize values that may not have the same value ranges so that you can work with multiple datasets, or you may just want to reduce the level of noise in your specific datasets. Either way, let's cover how to use GenAI for these types of operations. Welcome to this lesson on how to use GenAI to cleanse and standardize data. What are cleansing and standardization as activities? Well, they make a dataset more congruent by reducing inaccuracies, noise, and errors. In a way, they streamline data by reducing noise and by removing things which are not congruent and just confuse the data science or any other type of tool that wants to work with those data, and the humans as well that want to work with those data. But what is the general process here, even without generative AI? Well, first we identify the errors themselves or the biases in data. Do we have duplicates? Do we have typos? And so on. What are the sources of issues? Then we define the rules or the standards to fix those entries, right? For example, must all values be within a range? So we are going to standardize all of those values to be within that range. Or for example, we have specific codes for a specific field, and we have to take all fields that don't have a code and attribute one, even if by default. But either way, what are the criteria to fix a value, if you will, and to make it more congruent? And then we basically correct the entries based on the rules or standards that we have defined for them. And how can GenAI help in this specific case? Well, for one, it can automatically identify errors, right? GenAI is very good at dealing with typos and with other inconsistencies in text. Basically, ignoring those specific details and seeing the big picture and then correcting everything based on the big picture. So in many cases, GenAI by itself, even without needing a specific prompt, can already fix a lot of the issues in a dataset. Obviously, you want to guide it with a specific prompt, but chances are, if you just copy-paste a dataset onto a text generative AI model and you tell it to fix it, it's already going to do wonders for you. Or for example, it can also automatically recognize the value ranges and the standards themselves for specific fields. That is, GenAI is very good at reducing several entries to the same format or converting several values to specific categories. It's very good at standardizing values by itself. When you are performing cleansing and standardization with GenAI, what are some examples of prompting here? Well, for example, you can say, hey, please identify and correct the typos in customer names in the specific dataset. Or please standardize the date formats which are present in this column to always be the format year, month, day, and maybe add a new column that flags entries which are erroneous or not convertible. For example, if they don't have a date, or if they have dates that have weird values, such as, for example, having a value that is higher than 12 for the month and so on. So basically noting down what are the values that cannot be converted with this criteria and noting that down. And what are some best practices that we can apply here when using GenAI? Well, we have to prioritize the values that we want, because look, if you try to cleanse all fields at the same time, this can just generate entropy and problems. Maybe the LLM can't handle it, maybe the dataset is too large, or maybe you just run the risk of the attention of the mechanism being spread across too many things at once. So what you should do is focus on the highest impact values in one pass, and then maybe you do another pass for the lower priority values. But don't try to fix it all at once, because you run the risk of the LLM actually not fixing anything. And then having field metadata also helps a lot. That is, knowing what are the specific value ranges or formats that certain fields can have, right? And feeding that to the LLM. If you don't have this structure or this documentation, it can still work, but it's a lot better if you tell it explicitly, hey, these are the values that are allowed, and this is how I want you to do the conversion, because it makes life a lot easier for the LLM, if you will. It guarantees that the values abide by the rules or formats that exist for that field, and also it reduces a lot of the errors or hallucinations because the LLM has a very specific instruction for what to do for that type of field. And actually, we also have risks and limitations when we're using GenAI to both cleanse and standardize data. For example, it's possible to over-standardize in a way. Look, in some cases, we're not taking into account seasonal patterns or outliers or exceptional situations when we are creating the rules. This is not an error with GenAI, this is a human error, if you will. But look, if we use GenAI to automatically enforce these rules and standardize everything, which would be done a lot faster and a lot more efficiently than a human would, then we run the risk of ignoring that variety or those outliers or those unique variations that actually should be preserved. Again, this is not an error with GenAI itself, but because GenAI can standardize values a lot faster than if you ignore certain values and you consider them to be outliers when they're actually reasonable, then when you use GenAI, you can over-standardize a lot faster than a human would. But still, it's something to keep in mind here. And then you may have problems with domain expertise, because especially if the LLM has not been fine-tuned on specific domain knowledge, it may not know the specific formats or the specific terminology or the names or how certain things are standardized for specific formats, and it may create errors. For example, if you are working with a financial dataset, then you have specific terms and specific methods to calculate risk, to calculate revenue, and so on, or if you normalize certain values with certain formulas, if the LLM has not been trained to even recognize those terms or know what they mean, it's kind of a moot point to try and standardize those values with the vanilla LLM, if you will, right? So at least you have to provide some context. It could work if you provide a dataset and then a clarification of what the values mean and maybe the metadata on them and how certain conversions are done, but still, it's better if possible to have an LLM that already is fine-tuned to that specific domain expertise and the domain knowledge and the terms and the specific terminology as well, because otherwise it may just not recognize the words or the terms. This time, we're going to cover cleansing and standardization. So I prepared a quick dataset here that has a list of clients with phone numbers, and the phone numbers are in multiple formats, okay? Some of them have brackets while others don't, or they have a dash separating them while others don't. But at the end of the day, they're not in the same format, right? So what we're going to do is, as usual, work on these. Okay, so at a certain point, we have this global prompt and we're kind of just inserting the specific prompt within. Hi, DeepSeek. I would ask you to standardize and quantize the data in this data set. Let's just run it like this and see what it comes up with. It's taking a little bit to go. Okay. It's looking at the data. So what I decided to do for this sample data set was not just put the phone numbers in multiple formats, but also the company names are not standardized, right? Some of them are just uppercase. Some of them have the incorporation terminology like LLC, incorporated, etc. And let's see if it standardizes those and how. Again, it also depends on what you want, right? Do you want to have those legal terms in the company name too? Or it doesn't really matter, right? Okay. So first attempt, it's not outputting just the data set as we usually want. It may be the case that we actually need to repeat this for a couple of times. But we can already see, for example, that the phone numbers are in the same format. We did not indicate, in the case of variations, whether we would want one format or not. And we can also see that they're not exactly in the same format, okay? So let's do the following. Let's specify that we want the phone number to not have a country code and to be separated by dashes, okay? Please remove the country code from all phone numbers and output them as separated by dashes, please. Okay. So this was on me, right? Because if you think about it, the only thing that I wrote here is I would ask you to standardize and quantize the data set and quantize the data in this data set, right? So let's even be a little bit more direct, right? Please standardize and quantize. I don't know how the different politeness levels affect the results that you get, but we'll see. Okay. So did it standardize the company names? Not really. It didn't even remove the uppercase Amazon, right? So let's actually use a list of the things that we want to standardize, right? So specific fields. So phone numbers. Please remove the country code, yada, yada. And now company names. Please remove all legal terms, such as Inc., LLC, Corp, etc. Okay? And now let's see how it works with those. And you really have pretty strong wording when it comes to not output anything besides the data set. Here's the thing. I don't know what it understands as data set, but let's call it the table. Do not output anything besides the table as not to prevent parsing of the response. Please output just the table / data set. So I'm using stronger and stronger prompts to see whether they stick or not. Again, with probabilistic models, in a lot of cases, if you just prompt for something with more intensity, you tend to have it. And again, in cases where we are not obtaining what we want, we can see the thought process here and gauge whether it's aligned with what we want or not, right? So, for example, for the company column, without certain legal terms, etc., this is a bit trickier because it's not just about removing specific words, but ensuring that they are stripped from the company name. Okay, this actually seems reasonable. And okay, so it's not doing exactly what we want it to do. At least I can see that the company names are all in uppercase, which is a little bit weird, right? But they're not all in uppercase because it reaches a certain word and they start being lowercase. If I had to guess, maybe this Innovatech, because only certain words are uppercase, maybe that's how it is in the original data set, right? So 14. Okay, so 14 is not even Innovatech, it's Salesforce. Okay, so something here is a little bit wrong. So it's converting these. Okay, so this is weird, right? It's changing the company names. It's changing a lot in the data set. So you may have situations where it doesn't know what to do and it has a hallucination and the context just degenerates and it doesn't end up well. So what we can do here is we can break these into two, right? Into two passes. So we can have a first pass where we just say, for example, please remove the country codes from all phone numbers and output separated by dashes, right? And then what we can do is we do one first pass just for the phone numbers. Then we take the corrected data set and then we feed it again to the LLM to take care of the company names, for example, right? Again, because we are using an LLM version that is smaller, it may not have the capability to do what other LLMs would do that are, commercial grade LLMs. The pipes are back, the pipes are back for some reason, but this is still in the thought process, I think. Okay, so you can see that it's doing a lot of back and forth here, right? So it's thinking about extracting the digits and not putting them in the same format. Either way, what we can also do, worst case scenario, is we can take each element that has been fixed and, copy paste it into the data set. That's not ideal, but okay. It's interesting here that this doesn't match any of the data that we have. So this is, catastrophic failure over here. There might be something here that doesn't make sense. So as we're seeing, ABC Corp, Green Services, there's a lot of stuff here that is not what we inputted. So what we can do is we can say, for example, please output only the corrected phone numbers, because it could be the case where if it is in fact trying to change the whole data set, it doesn't have enough attention span in terms of the LLM in order to both correct the phone numbers and output the data set. So let's take the case where we just output the phone numbers, and maybe we can copy and paste this into an Excel sheet or a Google Sheets, and then we can just replace the columns with the ones that have been fixed, okay? Again, it could also be a limitation of this LLM because it's such a small LLM, but I don't want to draw any conclusions for now until we do have all of the information. What we could also do here is we can see that it has specific conclusions here, right? For example, replacing periods with hyphens, or there are spaces and hyphens, so converting those into dashes. What we could do is we could be more specific here, right, about the specific instructions. So if we go back to the previous version, I'm not sure I'm going to run this one. I'll see how the current one does, but we could say something like, output them as separated by dashes. Okay, remove the country code from all phone numbers, replace all periods and spaces with hyphens, and that's it, right? So if we refine the prompt in terms of the transformations that we want it to perform, then it's not going to need to have such a big thought process because, it already knows what to do. Because you can see that it's going back and forth here saying, hey, I'm going to convert these, and so I'm going to remove the country code, but I think that the correct approach would be to take the number without the parentheses, etc. There's a lot here, right? So what we could say is, okay, after removing the country code, we have a specific number. So it could also be the case where it may be mistaking the country code that starts with a plus sign with normal phone numbers that actually don't have that country code, right? So what we're going to do is we could say, please remove the country code +1 from all phone numbers if it exists, and then replace all periods and spaces with hyphens. Please output all phone numbers separated by hyphens. And we could see that it still hasn't finished the thought process from the previous version. Okay, so this is going back and forth here, right? We could also change the parameters of the LLM, but right now, this is just an illustration, right? I'm trying to show you how to make it work, okay? So in this version, we made it very, very clear what we wanted to happen to the phone numbers, period. And now let's see what it does, right? May also be the case that there are certain phone numbers here that have words, if I'm not mistaken, such as this one, 212-555 help. So some of these things could trip up the LLM, but we can see again that it's thinking a lot. Okay, the one that has a text, it's going to leave it as it is. Again, it's going through a very, very significant thought process. But again, I just want to show what the general process is, right? Depending on whether you're using an open source LLM or a proprietary LLM, on whether it has been fine-tuned on transformation operations and it knows how to replace certain things, depending on the terminology too, because do you call them hyphens, do you call them dashes, how do you do things? But yes, we can see here that the phone numbers are correct, but it's changing everything else but it's changing everything else about the data set, right? So we have, for example, this one, 212,555,1234. So it's correct, but everything else is not. Jennifer Smith becomes John Doe. It could also be the case that the dummy data that I'm using contains certain trigger words, right? For example, if somebody is called Smith, it may assume that it's not a real person. So it renames it to John Smith or John Doe or other usual terms that we use for anonymous names. But you can see that in this case, the phone numbers are actually being formatted correctly, but everything else is not. So this would be one scenario where it could be useful to just output the phone numbers and nothing else, and then just copy paste this on an Excel sheet, right? Apart from this, it seems like it's actually working, right? Or is it though? No, this one is not working anymore. So what I'm guessing that's happening is because it has such a long thought process, it's exhausting the whole context window and it forgets what the initial input was before it even finalizes it. Let's see if I could do something else here, which is say something like, please don't think a lot, just make the replacements and output the numbers. Here's the thing. We also don't need to have something that is perfect, right? Ideally, we would run it in one pass and all the data are corrected. But if we at least reduce the noise level, if somebody would need to do this manually, and now they need to do less things manually, that could already be good. Assuming that the LLM is not introducing errors instead of fixing them, okay? Let's see if this directive to not think a lot and just make the replacements actually changes things. Okay, so it's thinking a lot less, right? So this is the thought block compared to the previous testament that we have here. I don't even know where this begins, right? But you can see how the thought process is slower here, right? Now, for the acid test, does it work? It kept the parentheses, but it put the hyphen in this one. In this one, it added the hyphens, yes. In this one, it converted the periods to hyphens, yes. This one, okay, so far so good. The only thing that it's doing is it's not removing these. But the interesting thing is we can take these ones, right? We can take this output and assuming that all of this works after a if check, we already know that they're exactly the same, except that they have the hyphens here. One thing is that it did not convert the 20. So we could add another global directive here to say, please convert all entries and do not skip any entry. One thing that could also happen is, again, because I'm using such a small model just to show you what this is like in real time, it could also be the case that it doesn't have enough memory or context window to process all 20 entries. So we could do the first 10, start with the first 10, then do another pass just for the next 10 and keep going like this, right? When you run into resource constraints, you're going to notice that there's a lot of things that you can do. You can process just one field instead of multiple fields. Instead of asking to output the whole data set, you can just output those fields. You can do smaller portions of a data set instead of the whole data set at once, and so on, right? But you have a lot of options here. You can see how we're changing certain things to get us closer and closer to the target. So apart from the fact that it did ignore everything after the first 12 entries, it's in the exact format that we want. It's ready to copy and paste. It is in CSV format and it doesn't contain anything else, right? So we do have some fluctuation, but it's generally doing what we want. So as we see, GenAI can be a powerful ally in terms of cleansing and standardizing datasets. But it is important to understand that it can over-standardize data, and you also need to guide it in terms of what are the guidelines or the criteria to perform that standardization. Let's talk about data augmentation, which is adding additional information to a dataset. Maybe because it doesn't necessarily have low data quality, but you still want to increase its data quality so that you can use it for insights or for other use cases. And GenAI can definitely help here with its capability to synthesize and summarize conclusions and insights from other text-based data and then insert those into a dataset. Let's take a look at how this would work. Welcome to this lesson on how to use generative AI for data augmentation. What is data augmentation? Data augmentation consists of enhancing data that you may have with additional fields or metadata or other content. The data may not necessarily be of low quality, but they're going to be of even higher quality now because they possess additional information. And this can be metadata, for example, about certain trends or about certain summaries or aggregations, or it can just be additional context that can be used to explain certain fields. So what is our general process here? Well, first, we identify where data could benefit from more information. For example, for every customer that has a location, should we also add the average transaction value for that location and add it to every single transaction or every single customer in terms of averages, right? Where is it useful for us to add those additional data or additional explanations or additional content? Then we source or generate that additional data sources that may help. So in that case, if we want to obtain that average transaction value for a location, we have to obtain that information from somewhere, right? We have to calculate it. Maybe it's present in certain reports or so on. But after we decide the additional information that we need, then we have to source it. It's as simple as that. And then finally, we integrate or we derive the augmented data for this additional information, right? In certain cases, it's actual information that you have to grab and add in some way, parsing it. Or it may just be, for example, mathematical formulas where you already have the base values and then you have to calculate a specific formula to reach that additional field, right? Both cases can exist. And how can GenAI help for this specific use case? Well, for example, it can easily adapt contextual information. This is one of the biggest strengths of LLMs in general. That is, GenAI can easily process the additional data, the additional information sources for a specific purpose, and then merge them with the specific fields and generate those enriched fields, especially if you're using RAG. So LLMs are very intuitive, right? It's very easy for them to take a 200-page financial report and find things that are relevant to enrich those specific fields, and then include them and refine those fields with that information. They're very fast at parsing that information and making intuitive decisions about what should be added and what is relevant in terms of the context for a specific field or group of fields. And then they're also very good at inferring new features, right? GenAI can not only enrich the current fields that you have with the information provided, but it can also suggest new fields and new values for these, what we call feature engineering, right? As we stated, if you have a customer and you're talking about, for example, financial transactions, it could be good to have an average of that customer's financial transactions, which is a new feature, right? So GenAI can also suggest what are the useful features, which may be a combination of fields, a multiplication of fields, a normalization of a field by another value, and so on. Based on your specific purpose, it can tell you what it suggests for you to create in terms of new features. What are some prompt examples for data augmentation with generative AI? Well, you could say, for example, hey, please analyze this data set and suggest additional relevant fields or features that could enhance our understanding of these customers. For example, if you're trying to draw customer insights by location, by purchase type, and so on. Or you could say, for example, please analyze this data set of suspected fraud data and create a new field for the user IP suspicion level, if you will, the level of suspicion of a user's IPs based on the specific IP history of a given user, right? Are they logging in or purchasing from suspicious locations and so on, and then converting that into a quantified measure from 0 to 100, which can then be used in a quantified manner, for example, in a fraud prevention algorithm or other types of algorithms. And as usual, we also have a couple of best practices here. Well, one of them is to verify the quality of the additional data, because look, reports, public data, and many other data sources may be biased, or they may have incorrect information, or they may just be plain wrong in certain aspects, right? So just because the information is available, it doesn't mean that it's good. This is a general principle for dealing with data in general, right? So if you have a very high quality data set, but then you add additional information sources which are not high quality, they're not helping you. They're just diluting the quality of the data set itself. So just like you vet your data sets and they need to have high data quality, all of these additional sources also need to have high data quality, because otherwise they're doing more harm than good. And then we also have to ensure field consistency. That is, when you are generating new features or new fields, we have to ensure that the number ranges, the text formats, and others are all consistent. For example, if you have a field which is about revenue and it doesn't include certain elements or it's calculated in a certain way, you have to make sure that if you keep talking with the LLM and you keep requesting answers for multiple datasets, then you have to make sure that the meaning of revenue is the same as you continue to speak with the LLM and you get subsequent answers. Because sometimes you have context degeneration or certain things just change. Naturally, giving the LLM very specific instructions helps prevent this, but context degeneration sometimes changes the meanings of specific words, and that has consequences for your data operations, naturally. And naturally, we also have risks and limitations when we are using generative AI to augment or to enhance data. One of them is that it is possible to add clutter or add irrelevant data. Look, enhancing data means adding new actionable information, but you can't just add any information and call it enriching, right? Especially if the information is of low quality. So not just adding irrelevant details to the same data, right? You have to add things that make sense and that help you, usually with specific use cases. but knowing which is which may be hard. For example, if you have data for a specific financial report and you want to add certain elements of those data to your customer profiles, is that useful? Who knows? It depends on the use case, it depends on the data that you are having, and it depends on the quality of that report. So the lesson here is that you can't just add any information to a dataset and call it enriching. You truly have to be enriching it with worthwhile information. But it's important to vet that information to know what is truly worthwhile. And then, as always, it's dependent on the data quality. As we mentioned, right? If our dataset is refined, but we augment it with public information which are wrong or up to date, then it becomes equally bad. You have to vet the additional sources of information as well as you vet your datasets. And by the way, this is going to be a crucial lesson when we tackle RAG, right? When you are embedding all of these other documents in additional sources of information, it's crucial to vet that information, because otherwise that information is useless, or even worse than useless, it's actively going to be harmful when you are embedding them. This time, we are going to augment data using an LLM. So what we have here is a list of products, right? And what we're going to try to do is to infer the target demographic, for example, or other fields based on these products. So basically, we are going to try and extrapolate some insight or conclusion and then add to this data set based on that. Okay, so if we go back to our trusted prompt, okay, so we copy paste the data set here, do the global instructions that make sense. CSV format, do not output anything besides the table, convert all entries, do not skip any entry. We're not putting column names. There are no commas in the column names. Okay, so please augment this data set, creating a new column called target demographic that contains a gender and age range. I'm going to assume that it's in the same format, but again, we can just run this, see whether we like the result or not, and adjust based on that. Let's see what is the output that we are going to obtain, right? So you can see the thought process here, photography enthusiasts, male or female, 1834. So unlike the previous example, which was so complicated, this one is actually pretty simple, right? Again, we do have to vet this. Do these numbers make sense? For example, in terms of photography, are most people who are interested in photography between 18 and 34? And we also have certain things here that don't make sense, such as, for example, oh, they do make sense. I thought that it just included the female, but there's the male here as well. Again, we can also decide what is the format here. Do we want it to have, for example, male 1834 and female 1834, or do you want a keyword like both genders, for example? And actually, we're not even getting into other topics such as what are the keywords that we consider for genders, or are we going to eliminate certain biases, such as, for example, assuming that science things are for men instead of women and other things, right? So there are other possible inherent biases that we may want to tackle or not. It depends on what our scope is. But at the end of the day, this seems like it was a reasonable attempt here and we got reasonable results, right? So children's waterproof watch, 3 to 12, 3 to 12. I don't see anything major here that doesn't make sense, right? Or for example, yoga. We see male and female with the same demographic distribution. And again, right, there are other matters here that we're not considering, which is, do we want to consider a specific gender or age that we think that this product would belong to? Or do we consider the usual purchases, right? So are we going to perpetuate certain biases, or are we actually going to try and fight those biases? But as far as examples go, this is a very successful example of how to augment data, right? We're saying we want this new column and we want the LLM to create this and to extrapolate this information based on this. We're actually going to try and do something else here, which is we're going to try and make it a little bit more complex, right? Because this is gender and age range. And also, please add a new column called seasonal demand with the quarter of the year that we should expect the most sales for that product. Okay. Now this one is going to be a little bit more challenging, I think, because there are certain things that are associated with seasonality, but others that not at all, right? Such as, for example, the winter down jacket, that's obvious. But the gaming laptop, is there a time of the year where people buy more gaming laptops? I don't know. And again, there may be biases here. For example, is it going to assume that we sell more gaming laptops next to Black Friday because it's taking into account the usual Black Friday promotions, right? So what is true seasonality, if you will, and what is being considered due to other factors? So what did it? We do have a little bit of a bug here, but let's assume that that is fine. Okay, so these are the results. Okay, so the professional DSLR camera is going to be in Q1, Q3. It could be good to introduce a new field here that has the justification, but I'm getting a little bit nervous because if we ask it to do a lot at the same time, sooner or later it may blow up, okay? So let's do the following to illustrate how we would do it in certain passes. Let's take these current results that have already gone through one pass, and let's say, please justify the state of a man that exists in every product present with a new column called justification. Again, what we're doing is we're splitting this into passes, right? We got the results from the first pass, we saved those results, and now we're building up on top of that. And this is good because now the attention mechanism for this answer is just going to be focused on this justification, right? It's not going to be doing more things at once and probably blowing up the whole thing or having a big hallucination. So, what are the justifications that we already see here, right? Professional photographers often travel and need new gear during spring and summer when outdoor activities increase. That can make sense, right? But it's in Q1, Q3. Q1 is winter, if I'm not mistaken, because it's January through March. So if it's going to be spring and summer, it should be Q2 and Q3, right? So not exactly the same. So this is also a lesson, right? Which is when you run this through an LLM, are you going to blindly trust the results? Or are you going to vet it and make small changes here and there, right? And at the end of the day, you shouldn't expect this to take care of every single thing that you have to do. This is not properly formatted. But if it saves you a lot of time, then that's okay. For example, if it says it's Q2 and Q3 because it's outdoor activities, that already does a lot of the heavy lifting, right? Because you don't need to be augmenting those data by yourself. So in certain cases, even if the LLM doesn't do everything by itself, and you still have to, change a small detail here and there, that could already be good because it already saves you a lot of time. But in other situations, when you are dealing, for example, with health data, maybe it's not acceptable at all to take these results without vetting them in 50 different ways, right? Again, it depends on the use case and it depends on what you want to do with the LLM. So as we see, GenAI can definitely be used for data augmentation, but it is important to understand that the quality of the information is going to be the biggest bottleneck. Because if you are inserting insights based on information that is not relevant or not accurate, well, garbage in, garbage out. Let's talk about using generative AI for statistical analysis and detecting anomalies. In certain cases, you may have data sets where certain values just don't fit, or you may want to just analyze what is the distribution of values for a specific column or a specific field. And GenAI can help you with this. Technically, it's not statistical analysis because it's not a statistical model, but it can help find the outliers and it can help find the distribution of values for certain fields in exactly the same way. Let's take a look at how GenAI can do this. Welcome to this lesson on how to perform statistical analysis and anomaly detection using generative AI. When we talk about statistical analysis of data, we're usually talking about doing a preliminary analysis of what values exist in their distribution. What is overrepresented? What is underrepresented? What are the outliers? What are the biases? What are the values which are empty? What is the percentage of values that don't have specific entries? And so on. So what we're talking about is about doing data profiling in a way. Usually you can do full-fledged data profiling if you have the time and you have a dedicated team. But sometimes we just want to perform a preliminary analysis, right? We just want to take a data set and then in 5 minutes conclude, hey, we have overrepresentation of this specific feature or this value, we have these outliers, and so on. So you can do statistical analysis with various levels of that, but the general process is very much the same. So optionally, we may define the expected value ranges or choices. So what I mean is, you may have data that you already know the schema for and that you already have the metadata for, so you know exactly what the values are supposed to be and what are supposed to be the specific formats and so on. But you can also do statistical analysis on data that you don't have this information for. Naturally, it's not going to be that easy, but it can be performed. So this optional first step is because if you don't have this information, it's definitely going to make your life easier and you should use it. But you can use profiling and statistical analysis without having these specific formats and schemas. It's just going to be a little bit harder. Then we actually perform the statistical analysis, right? We analyze the existing values to understand the value distributions, the summary statistics, correlations, outliers, and so on. So basically, we're using statistical models to calculate what are the values, what are the correlations, what are the biases, and so on. What are the conclusions that we can draw on a statistical level from the data? And this is the final step, right? We draw those conclusions usually using a statistical model before the advent of GenAI. Now, how does GenAI change this picture, right? What can it do for us in terms of detecting anomalies and performing statistical analysis? Well, GenAI can easily summarize things, which is a big advantage here, right? GenAI by itself can already do a simpler version of full-fledged statistical analysis or data profiling. It's able to summarize trends, to detect unusual values, and other obvious issues, if you will. It doesn't perform pure statistical analysis, it performs a more kind of intuitive analysis based on text patterns, but it doesn't make it any less valuable. It's very good for when you don't have the manpower or the resources to perform full-fledged statistical analysis, but you can still take an LLM, dump a dataset on it, and ask, hey, what are the issues here in terms of biases, values, outliers, and so on? And it can still give you valuable insights. And then GenAI is also good at tailoring the specific analysis to context, which is good, and statistical models don't usually do it. That is, GenAI cannot just analyze whether the values make sense or not, or what are the outliers, but also for a specific context, right? For example, do these transaction records make sense as holiday season purchases, right? If we have outliers, if we have values which are empty, if we have an overrepresentation of a certain type of purchase, we can analyze it not just from a general standpoint, but specifically from a holiday season purchase standpoint, right? Does this data set make sense for this time of the year? And you can run those two analyses in parallel, right? You can ask an LLM, what do you think in terms of statistics in general, but also for this specific context of the holiday season? What are some prompts that you could use to perform this type of analysis with GenAI? Well, you could say, hey, please analyze this dataset for outliers and try to provide a justification from context for the existence of each. And if you can't, then maybe that outlier is a wrong value. Or you can ask, for example, hey, please identify a trend or a historical change in the values provided over time and summarize it. So as you see, we're using precise instructions for the type of statistical analysis or just analysis in general that we want to perform of a given dataset. So you can have a specific focus in terms of the values, the historical evolution, and more. But basically, we're dumping a dataset on an LLM and asking it, what do you think and what doesn't make sense here? Or possibly, what doesn't make sense from this specific standpoint? And as usual, we do have some best practices here to perform this statistical analysis with GenAI in the best way possible. So first, you want to combine this with actual statistical analysis, right? GenAI can provide summaries, but statistical analysis itself can provide in-depth breakdowns for the best of both worlds, right? You can compare the conclusions that are drawn by two types of models. And in certain cases, GenAI can draw wrong conclusions or it can ignore certain values. It probably is not going to do it, but with an LLM, you know that there are hallucinations and others. So GenAI is a little bit different. It can provide conclusions and it can tailor to the context, which statistical models can't, but then statistical models have a depth that GenAI doesn't, right? So using both models, if you have them available, is what you should do in order to have those two perspectives that you can then reconcile. And also, you should define the expectations for that analysis, right? As we find outliers and trends in similar datasets, we can refine the prompt with ease. So you can tell the LLM what are the usual outliers or the usual biases. In other words, what to already expect in a way in terms of issues and what are truly never seen before situations, right? So you don't just need to do a general analysis, if you will. You can already tell the LLM, these are the problems that we are already expecting to find, but please flag especially the problems that are not the usual ones. In a way, you are adjusting the expectations of the LLM when it's performing the analysis. And also, we do have some risks and limitations when we're using GenAI to perform this type of analysis. So one of them is that you may have false positives or negatives. The definition of what is a justified outlier or unjustified outlier is already pretty blurry, right? You need to find justifications for certain outliers, but in certain cases, you don't know whether this outlier does make sense or whether it's false. So in complex datasets with a lot of noise, GenAI can wrongly flag values as being an outlier or miss those outliers altogether. And just like with any other type of AI model, there are consequences to having false positives and false negatives. And based on your specific use case and how sensitive those conclusions are, you have to be the one to decide how aggressive do you want to be in terms of flagging those outliers or any other type of issue. But then there are all of these other types of issues that pop up as well, right? You have enough manpower and enough resources to hunt down every single one of those issues, or are you going to look at them in depth and so on, right? But in general, you just want to keep in mind that just like for any other type of AI model, there are consequences to false positives and negatives, and you have to be aware of them. And then the results are not good without the context, right? Simply dumping a dataset on GenAI without clarification of what are the fields or the context itself limits how good the error detection is going to be. The biggest strength of GenAI in many ways is also its biggest weakness. That is, if you provide context on exactly what this dataset is, what is the historical time period, or what are the conclusions that you are expecting to find, then it can tailor the analysis. But the flip side of that is that if you don't have any context or backup information or information about what the values mean or what the features mean or the value ranges and so on, then the analysis is going to be very limited because GenAI doesn't have any context at all, and therefore the insights are going to be very limited as well. In this lesson, we are going to perform statistical analysis on data. That is, we are going to find out what are some patterns in this data set in terms of what are specific peaks or valleys, or what are specific anomalies that don't fit the standard, if you will, and try to find out a justification for each of these. So in this case, we have a data set of website traffic per specific day of the week, and it spans a whole month, if I'm not mistaken. Okay, so what we're going to do is very simply go to our prompt and say, "Hi DeepSeek, please analyze this data set and tell me what are major anomalies or values that don't make sense." And this could be an interesting use case because it's less demanding. You don't even have to output the whole data set changed in some way. You literally just have to analyze it and say, what are the conclusions that you are drawing? And let's see if it makes sense. To be honest, this is a data set that is very, very hard to interpret, right? Maybe you could plot it or you could show it in a visual manner in some way to make it easier to understand, but it's very, very hard to understand as is, right? How do you interpret this, number of visitors or these specific spikes or values, right? It's very hard to understand these numbers without a specific context, right? So this is why a good idea is to take this, identify what are the anomalies or the issues that we may find, and then gauge whether they are true anomalies or not. Okay, so one small detail here, which is my fault. In these global instructions in terms of the prompt, there's a portion here that says, please output only the data set. But in this case, we don't want that at all because we wanted to output statistics, right? So our global prompt was actually not a global prompt. It was a prompt that makes sense for most scenarios, but not all scenarios. Okay. So here, the actual thought process of the LLM is very useful, right? Because it's saying, I want to understand what each metric represents. There is definitely some variation day to day. From March 1st to March 24th, everything seems consistent. But then starting on March 27th, something odd happens. The page views jump a lot. Well, do they? Which one is the page views? I think it's the third field. So 1500, 3200, 4600. It depends. I won't say that they jump because we do have a lot of 45, 31, etc. I think they actually have a low on Friday and Saturday. But is that normal for Friday and Saturday? No, because other Fridays and Saturdays actually have high values, right? So it's slightly different. We see some spikes, we see some drops. Okay, so what are the major anomalies? Significant spikes in page views starting from March 25th. We do have certain spikes, but I wouldn't say they're starting on the 25th, they're starting on the 28th, right? Because we have 9800 here, 8700 here, 6500 here. Yes, but we do have another spike here, right, between the 15th and the 17th. So there are different ways to interpret this as well, right? We then have specific demands in terms of, is this an anomaly in the long term? Is this an anomaly for this week? So maybe being a little bit more specific about that as well could help. And again, plotting this on a graph and seeing this visually represented could be interesting as well. So here's what we're going to do now. We're going to make this a little bit more advanced. We are going to leave this part because I need to crop it later. We are going to take this customer purchase behavior data set and we are going to add it here. Okay, so what are we doing in this specific example? We are taking an additional source of data for context. Why? Because if we have this information about the purchases, we can verify what anomalies in terms of, for example, higher page views are associated with a higher level of purchases. So there are times when we did have more traffic on our website and we had more purchases versus other things that may just be anomalies, right? Maybe a marketing campaign, maybe seasonal demand. But at the end of the day, the list of purchases is going to help us give a little bit more context to this website traffic and tell us what makes sense, right? So I do also realize that I didn't give it enough context, right? It can infer from the column names, but we can specify, right? These are two data sets, one of website traffic per day for a given month, and another one of customer purchases in that month. And now we can also go a bit deeper on the anomalies, right? Please identify which anomalies are associated with high page views and sales, and which are anomalies in the numbers of page views without a corresponding fluctuation in customer purchases. Okay? I would say changes, because we don't want just the higher page views and higher purchases. We just want the fluctuations in general, right? Which anomalies are associated with changes in page views and sales, and which are anomalies in just page views, in just the number of page views, or just the sales without a corresponding fluctuation in the other property. Okay. And now let's see what it says, right? I'm hoping for something that is a little bit clearer, right? So we can see here that it's interpreting the two tables on most days. There's only a few instances where the technical issue element changes. By the way, this is very good, because if we know that there's a specific technical issue in this new table, then we can associate it with a type of change, right? For example, if the page views drop a lot and there is a technical issue reported, then it's probably related. Okay, so analysis. So is this just an analysis of the anomalies in the technical issue? There's only one instance where the technical issue changes from no to yes on March 24th. And from March 25th onward, the field returns to no, maintaining consistency after the anomaly. Okay, so it is detecting a high level of page views in this last part of the month, but I'm still not satisfied because it's just in these 3 specific days. It's not on the 25th in specific, right? But it is when a technical anomaly happened, and we can see that on the 24th and 25th, we do have lower views than usual, and we do have a technical issue, right? Okay, so yes, on the 24th and 25th. So at the end of the day, these 2 lower numbers are in fact due to a technical issue. But I don't want just that, because it's just focusing on that. Again, it may be a limitation of the LLM, because maybe a smaller LLM like this one, or because it's not fine-tuned, it can find a lot of anomalies at the same time. So it's just focusing on one thing, which are the technical issues. So let's actually split both of these, right? Please identify anomalies associated with technical issues, but also anomalies not associated with those. And let's see if it finds something else that we are not identifying yet. My dream, right, my hope is that it's going to identify this specific part after March 28th, when we do have a major spike in page views that is not justified. That's the dream. And we are prompting hard in order for it to separate the types of anomalies, right? So traffic fluctuations, high spikes on March 28th and March 29th. Yes, this is exactly what I wanted, and it's finally giving it to us. So March 4th shows notably low activity. Does it though? Not really. March 4th showing 70 to 130 views. No, that is literally not true at all, not even close. But okay, the high spikes show the surges. Okay, a dip in bounce rate on March 4th, then returns to normal levels. Does it though? So the bounce rate, 34, 33, 34, 36. Okay, so for some reason, it's focusing on March 4th, and March 4th is not showing what it's seeing. So do we have increased revenue on March 3rd though? So I'm vetting all of the conclusions that it's drawing in order to kind of vet this, right? So 3.2, I'm assuming that this is in thousands of dollars, 3.2K, for example, 3.4K, increased revenue on March 3rd, approximately 7K. No, not at all. It's 3.3. Unless there is something that I'm missing here, but I think not. So as we can see, there are certain things that it detects as anomalies, which are not anomalies at all, but then there are others which do make sense, which is why it's always good to validate the output of an LLM instead of just allowing this to go in a pipeline and to run unchecked and to actually make changes to production data, right? So in many cases, we can see these recommendations by an LLM as actual recommendations instead of being ironclad conclusions that we have to obey, right? But it did get right the part about the March 28th and so on. But do notice that in a lot of cases, what happens is you get the first result, which is it's obsessed with the technical issue. Why? Because maybe it's a language thing. Maybe it's associating anomaly with issue. And because there's a technical issue, immediately it jumps to, the conclusion that anomalies must be related to issues. But then when I separated and I said, hey, please give me the anomalies related to the technical issues and not related to the technical issues, now it split them across these two things, across these two dimensions, if you will. And now it gave me what I wanted, which was this period of March 28th to March 30th, right? But at the end of the day, we can still see some small hallucinations. Again, I don't know if it's based on the model. I don't know if it's the fact that we're using such a small and fast model or if it is something else. But yes, it's already giving us a lot of what we want, but not everything that we want. As we see, GenAI can help you perform this type of statistical analysis or a type of surrogate analysis that serves instead of statistical analysis. It's important to understand, however, that it's very intuitive, so you may not always have transparency on why a specific outlier is considered justified or not, and it's also based on context as many other LLM operations, right? The more information that it has in order to draw a conclusion, the higher the confidence level in terms of that result being appropriate. Let's talk about how to use GenAI to find biases, fix biases, and smooth datasets. You may have cases where you may have noise, or you may have underrepresented values or overrepresented values in datasets, and we can definitely use GenAI to both find out what are these biases and actually correct them. Let's take a look. Let's talk about how to perform the debiasing and smoothing with generative AI. When we talk about doing debiasing or smoothing of a dataset, we are talking about correcting imbalances or removing noise in a dataset to make it more fair and accurate, to basically streamline that dataset, to remove anything that doesn't make sense or that shouldn't be there, or that makes the dataset more heterogeneous than it should be. So what is the general process to debias and smooth the dataset, even before GenAI? Well, first we identify the potential biases, right? Do we have skew distributions of values? Do we have overrepresented categories? Do we have features that don't have any values at all, or where most entries don't actually have a value, and so on? And then we simply adjust the dataset based on the problem that we have, right? We may remove certain entries, we may oversample certain categories or certain entries that were underrepresented to begin with. To balance the dataset, we may generate synthetic data for exactly the same purpose, and so on. So we're kind of chopping up the dataset and picking it apart and thinking which portion of this should be reduced and which portion of the dataset should be amplified. And actually, GenAI can help here, right? Otherwise, there wouldn't be a lesson in this course about this. So how can it help? Well, first, it can detect biases, right? In terms of profiling or analysis, GenAI can immediately detect what are overrepresented values and what are other biases by itself, right? You can immediately dump a dataset on an LLM and it's going to tell you, hey, this specific feature mostly has this value. Maybe it's overrepresented. And the same for other types of usual issues, if you will. So it's good at flagging these problems. And then GenAI is also good at filtering noise itself, right? So if you tell the LLM, what are the values that matter and what are the values that don't matter, it can sample the dataset in a way that keeps the important values in just those values. For example, if we're talking about customers, for example, for a lending dataset, and the location really matters, but other fields such as, for example, the person's name or their address doesn't matter at all, only the aggregate location, then you can tell GenAI, hey, can you please balance this dataset by taking the underrepresented locations or the job income or whatever it is and making sure that the dataset is diversified in terms of these values. And you can have any values that you want for the other features that don't matter. So it's very good at prioritizing features in a way. You tell it these features matter, so please rebalance the fields for those features and please ignore all other features or don't care when you are rebalancing. So what are some examples of prompting when you are debiasing or smoothing with an LLM? You could say, for example, please analyze this dataset and identify the overrepresented values for this specific feature, such as customer location, customer income, or any other type of feature. Or, for example, you could also sample a sub-dataset of that main dataset that has equal representation of values, right? You can say, hey, please sample 50 values from this specific dataset that have an equal representation of values across these specific features. For example, job income and customer location. And the representation of other features doesn't matter at all. but keep the representation of these two balanced in specific. And naturally, we do have some best practices here as usual. So one of them is to provide context, right? Telling Gen AI not just to find biases, but to find biases taking specific things into account, such as domain expertise or business logic or expected value distributions helps here, because sometimes it even gives you suggestions that you didn't even think of. So in our example, if you're trying to normalize a dataset based on the job income and location of a specific person for lending purposes, maybe the LLM itself is going to tell you, hey, shouldn't we normalize the job income by the location? Because different locations may have a distribution of wealth that is different from other locations, right? So it can suggest you to create a new feature that actually normalizes the job income by a specific factor from that location. So giving the specific context to the LLM when you are asking it to debias or smooth the dataset is good because it can give you suggestions or it can tune those values to the specific context. And then backing this up with data profiling, right? Gen AI can make mistakes, right? So running a quick data profiling task for value distributions just to double check that Gen AI really made the job well done, that can help here. In many cases, if you can run the traditional model at the same time as the Gen AI model, then you can kind of double check what it's doing, or at least in the beginning stages when you are still doing prompt engineering and figuring out what are the prompts that generate the best results, you can use the backup model for data profiling to ensure that the Gen AI results are good. And you can even do A/B testing to figure out what are the prompts that get you the best results, right? But either way, having a model that has another way of reaching the same conclusion, just double check the results of the LLM is always a good idea. And surprise, surprise, we do have risks and limitations when we are using Gen AI to smooth the dataset. For example, it is possible to over-smooth data, right? Just like when we talked about over-standardizing, when we were cleansing and standardizing data, it's also possible to over-smooth noise. Look, if we try to flatten the value distributions with too much intensity, we may destroy the variety in values that exist to a certain point, which prevents us from generalizing conclusions or insights. Sometimes a dataset seems messy, but it just means that it has variety, and that variety is essential. When we start cutting certain things that don't make sense because we want to make the dataset a lot smoother, in certain cases, it becomes too smooth, and then anything that we do with that dataset is going to be overfit because that dataset is not representative anymore. So sometimes the messiness in a dataset is supposed to be there, but the only way to know is depending on the use case and naturally taking insights with the various versions of a dataset based on what you take away from it or add to it. But that is the lesson, right? It is possible to oversmooth data and you don't want to do it, which is a challenge because you never know when you are smoothing data too much, right? And then we may have less interpretability with Gen AI. And this is something that you are going to find in common with many operations when you use Gen AI instead of the usual model for something, which is even with very clear instructions on what to oversample or what to undersample or what to do, Gen AI is going to be less transparent than a statistical model or other method, right? So if you tell Gen AI to fix a dataset and to balance it by oversampling a specific section, it may do it, but you are never going to truly know what it actually did unless you go back and check every single thing. Other models, such as statistical models, are clearer, right? They're very transparent. They tell you exactly what they're going to do and how they're going to do it. LLMs are more intuitive. They kind of have a black box magic to them. They do exactly what you tell them to do, but in many cases, you don't really know how they did it or whether they actually did it or whether they did 99% of that task or 90%. They did something that really looks like what you ask, but in many cases, unless you really look deep, you don't truly know that it was exactly what you asked. This time, we're going to take a look at how to debias and remove noise in a specific dataset, that is, fixing the imbalances that we may have in some way. So, we have this table here, which again is another dummy data table that contains job applications. And what we want to do is, let's say that we want to train an AI on the job applicants, right, on their data. And so we want to debias in terms of the education level or maybe the actual location or job role and so on. We want to make sure that our data set is not biased and we want to remove noise. And this can be achieved in one of two ways, right? We can either cut some of the entries which are overrepresented so that it's more balanced, or we can create synthetic data to augment the underrepresented portions and make it more balanced. But we are going to try both with an LLM. So we go back to our prompt, which was very big in the previous lesson. And we are going to copy paste this, and we are going to say, hi DeepSeek, please resample this dataset as to balance it according to the education level. I'm wondering if I should go deeper and say, please sample less of the overrepresented education levels and sample more the underrepresented education levels. Again, do notice that this is a very specific use case. In the real world, maybe you would have a situation where you just want the data as is. But here we are assuming that we want equal representation of the different education levels or the specific years of experience because we want to, for example, train an AI on all of the different candidates and we don't want to bias them, right? But there may be cases where you do want those overrepresented or underrepresented portions, right? If you're trying to fight bias, for example, in your organization, maybe you need to obtain the raw numbers before you actually start normalizing the data set. Either way, let's go to DeepSeek. Let's feed this as a prompt and let's see what it says, okay? So it's analyzing the entries. Let me just do a quick check and see whether it's actually true or not, okay? So PhD, we did find 5 matches. Masters, we did find 7 matches. It's not exactly what it found. Bachelor, 6 matches. It found 5. Associate, yep. And MBA. Well, an MBA would technically be a master's, but we didn't specify that, so we can consider it its own level. So we can see that it's not exactly the same in terms of the distributions that it's detecting, but it is close enough. And again, this is an open source, small LLM. It could be the case where you could use a plugin for it to process numbers and make the calculations better, but for now, I think that it's going to be okay. We can see that it's thinking a lot in terms of how to sample, but maybe that's a good thing, right? For the PhD entries, keep all 5. For the masters, randomly select 4 out of 6. Bachelors, keep all 5. Associates, keep that one. MBA, keep that one. I wouldn't be satisfied with this because if we are speaking, in actual honest terms, we may want the associates to be higher and the MBA as well, right? So what is the result that we got? We got a result of 7 entries. Are they balanced though? Well, we have 3 PhDs, 1 master, 3 PhDs and 2 masters. So this is definitely not balanced at all, okay? This is definitely not balanced. Keep one. So let's do the following, okay? Let's go deeper and let's say, please ensure that the output dataset has the same number of educated levels for all levels, period. Exactly the same number for all values. And let's see whether this forces it to actually take this into account. You can see that there's a lot of back and forth here. I think it's categorizing the numbers by the type of education level. Here's the thing. It's already going in the direction that we want, right? PhD, we have 5. We need 2 to make it 7. Masters, we need 7, right? Bachelor, 6. So we need 1 more. MBA, we need 6 more. Okay, so it's getting, its target is to get 7 entries for each, which sounds good in theory. Let's see if it does reach that level in practice, okay? Okay, so it seems like the thought process is okay until it reaches this point where, for example, on the MBA, it says we can't sample more than that. Yes, we can. You can repeat entries, but maybe I didn't make that explicit, right? So, okay, this is not that good, right? And I think it didn't even output the data set. So the same number for all values. Feel free to repeat entries. So my dream would be to ask it to generate synthetic data to make up for the entries which are missing, which could be a gamble, but let's take that gamble, right? We have nothing to lose. It's already kind of spinning its wheels and it's not giving us everything that we want. So I would say, please generate new synthetic entries for underrepresented education levels. In certain cases, we can even do the pre-processing to make it easier for the LLM. So we could count those education levels ourselves and indicate how many of them are missing and tell it, hey, you want to create 6 more copies of the associate level. You want to create 6 more copies of the MBA level. Why? Because that's one less thing that it needs to think about. And the attention span, the attention mechanism of the LLM is less diluted among different things, right? That is something that we could do as well. But let's see how this one goes, okay? So we can at least see that it's outputting a reasonable number of entries. So it seems good so far. But let's not count the chickens before they hatch. Let's copy paste this later and see how it goes. Okay, so we have this data set, right? We can assume that the first entries are the same, but I'm not sure that they're the same. So we're going to take a look at that later. So I'm going to temporarily cut that because I want to be able to count this. So we have 2 MBAs. How many associates? 1 associate. We have 8 bachelors. We have 6 PhD. And we have 8 masters. So we can see that it's not working that well. I think that the issue here is the actual counting, right? Without a math plugin, a lot of LLMs just don't work that well. I am tempted to just copy and paste this into ChatGPT or Claude to gauge whether it works better or not, right? I'm giving you just a simple example with an open source LLM, very small model. But let's try, for example, to count them ourselves, right? So say something like, we have 7 masters, how many bachelor? 6 bachelor levels. Bachelors, how many PhDs? 5 PhDs, 1 MBA, and 1 associate. Let's see whether feeding the actual numbers would work. Or let's actually say, please generate 6 synthetic entries for associate and 6 synthetic entries for MBA. And let's see how it deals with those. Again, what we're doing is we're taking a little bit of the work and we're pre-processing that work ourselves on a human manner to make life easier for the LLM, because now at least it knows exactly what it should do in terms of numbers. Again, without a numbers plugin for the LLM, this may be necessary because it doesn't deal with those numbers that easily. We're also building on the worst case scenario, right? We're using an open source and fine-tuned, very simple and very small model to try and achieve something very big, right? Which is literally data set balancing and, balancing according to one specific dimension. So this is the type of thing that would fail in a lot of cases, and we are trying to take it as far as we can in general. So it doesn't seem like this is working that well. Again, it's spinning its wheels. Okay. So what we're going to actually do is something else, right? We can break this into parts and we can ask it to just output the synthetic entries for the MBA and the associate. That's it. And then what we're going to do is we're going to take those synthetic entries, copy and paste them onto the base data set. And then once we have that complete data set, then we're going to try to resample it again, right? But even then, it's thinking a lot, right? But at least it's a little bit less than in other situations. But again, it's not formatting the data set in the way that we want it to. Notice how with this attention mechanism, in a lot of cases, if you wanted to do an extra thing, that it takes more of the attention span of the LLM, and then it doesn't do other things. So if you try to add a lot of things into the mix, if you wanted to output the data set in a given format and count and generate entries and do this other thing, the more that you want it to do extra things, the less that it's going to do the original things. Because it's a probabilistic model. It will probably do all of those things, but there's a chance that it's going to forget one of them to focus on another thing. So it did generate, right, these new entries. And I do think, yes, that it does have the associate level. So let's see, for example, whether the years of experience makes sense for this associate level, right? So the associate level that we currently have has 6 years of experience. And here we see 8, 6, 9, 12. Okay. So it's around the same level, right? And with the MBA, 19, here we have 15, 10, 12. It could also be the case that because we are running both of these education levels in the same answer, it's kind of averaging both of them as one. Okay, so let's do something else here, right? This could also be confusing because we are saying, please resample the data set, please generate the new synthetic entries, and here we say, just generate the synthetic entries. So what we're going to do is something very simple, which is, I want to save the global part of the prompt, right? But let me just cut this out and let's say, hi DeepSeek, please generate 6 new entries for the MBA position, which are similar to the existing one in the CSV format. please generate only the dataset table as the output and no other text. And so what we're doing is we're breaking this off into individual pieces, right? We're going to generate the added entries for the MBA, then the added entries for the associate level. Then we're going to get everything together. And then we're going to say rebalance the data set now that it has all of these. The dream would be to have all of them at the same time, but I'm not sure we can, right? So 6 new MBA positions. Well, if they are MBA positions, why do they say masters or bachelors instead of MBA? This is getting a little bit frustrating, okay? It seems like it doesn't have enough attention span or enough parameters to take care of this task very well. So all of them positions should be MBA level. Please ignore all other education levels. I think that what's happening is also when you're running synthetic data, when you're trying to create synthetic data, you have to say, what are the fields that stay the same and what are the fields which are supposed to change, right? So now we get MBA, right? As with a lot of things in life, if you just prompt hard enough with brute force, you are eventually going to get it, right? Okay, so it didn't generate it in the exact same format, but yes, let's do this. So please ignore education levels. Please generate the new entries starting with ID A021 with the same fields and in the same format as existing ones. And you can already see how the attention mechanism is split here again, right? Because we're asking for two things which are a little bit contradictory. We are asking it to have a variation of values in the same format as all of the other values, but they all have to be MBAs, right? So there is kind of a fight between these two requests here, which is on one hand, they all have to be MBAs, but they also have to vary according to the characteristics of the other people in the dataset, but they still have to be MBAs, right? This is the equivalent of having a generative image AI and trying to ask it to generate a man with black hair and at the same time generate a woman. So what is it going to do? Is it going to draw characteristics from both genders, or is it going to not use the black hair or to use the black hair and maybe to have more masculine traits versus feminine traits? We're having a prompt that has two components which are a little bit at odds with each other. So ideally, we will get what we want by brute force, but we're not sure. Okay, right? So it did generate these elements, right? What are the years of experience? The original one has 19. This one has 10, 12, 8, 15, 6, 14. The years of experience are a little bit below, but this is actually reasonable, right? Do we like these names? Maybe, right? Maybe we do. Jane Smith, John Doe, maybe because we're using the expression synthetic data, it knows that they are fake people, and so it's attributing fake names to those, right? But at the end of the day, now what we would do is we would repeat the same for the associate level until we get what we want. And as you see, it can take a couple of tries because we just have a data set that is either more complex than usual, or we're just asking too many things at the same time. But ideally, this is how you would do it, right? You would ask the LLM to either undersample the characteristics that are overrepresented or to repeat and oversample the ones which are underrepresented, right? So this is how you would reduce that noise and remove the biases in the dataset. Another thing that you could do, I guess, which we did not try in this example, would be you could run one pass to get the LLM to tell you what are the imbalances in terms of statistics, note those down, and then fix them one by one, or fix some of them with the LLM or some of them in a human manner. But this is how you would do it. So as we see, GenAI can help us with this type of operation as well, both finding biases and fixing biases in datasets. But do remember once again that it is very intuitive, so it is possible to not have a lot of transparency. And also, it is possible to oversmooth data. So really make sure that if you have a bias, it really is a bias and not just a perceived bias by the LLM. We are now at the end of this module on remedying data using GenAI. Let's take a look at the content of this module related to data remediation operations with text generative models, as well as cover our key takeaways this time. And with this, we are now at the end of this module on how to perform data remediation with generative AI. What was our major focus in this module? Well, automatically identifying biases, statistical imbalances, erroneous values, or other sources of issues in data using GenAI, in many cases as a substitute for a statistical model or other type of analysis model. Or how to actually deal with data sets that need to be fixed, right? That may have biases, incorrect values, overrepresented or underrepresented sectors, noise, or other imbalances, and actively addressing these. In other words, how to fix data with GenAI. Or how to add more information to entries or refine these entries by adding additional information to these. What are the main points that we take away from this module? Well, it is possible to remove outliers or errors and other unusual values, but we may be removing legitimate values. This is also a problem when we are doing it with human effort, but still it's a problem with GenAI as well. So it's important to know what is the context. Something that is an outlier in general may not be an outlier for this specific context. So it's also important to keep the context in mind and to know that something may not be an error and that it may belong there. Then it's crucial to add context or domain expertise, because the LLM may not know how to correct something in general if it doesn't know the formats, the meanings, the context, and so on. The more context that you give an LLM, the more efficient the measure that it's going to take, right? Whether it be an analysis or actually fixing errors. And remember the flip side of this, the less context that it has, the less efficient that analysis is going to be. Then, these measures may have limited efficiency for complex data sets. It is possible to overwhelm an LLM, right? So tackling several biases at once, trying to address many error types at once, dealing with gigantic data sets, and so on. All of these can overwhelm the LLM. All LLMs have an attention mechanism and they have to split the attention across the multiple aspects of the task that you tell them to do, right? So you can overwhelm the attention mechanism and you shouldn't. So the simpler the task, the better. If you need to do multiple passes for multiple operations, yes, it's going to take more computational power, but at least the job is going to be well done. Then, some of these measures may be less interpretable than if you use the traditional model for their counterparts, right? So GenAI can address a lot of issues, but it's not going to tell you how. It can detect biases or outliers, right? It can remove elements from a dataset and output the final dataset, but it's not going to tell you what were the criteria that it used to remove those outliers. Even if you gave precise instructions, you never truly know whether it did exactly what you wanted it to, or whether it just did something that was very close to it. And like the traditional model counterparts, which usually are very interpretable or explainable in terms of their results. And with this, we close this module on using GenAI for data operations at the remediation stage in specific. We are now at the data transformation module, where we are going to cover how to use GenAI for data-related operations when you are trying to transform datasets themselves, detecting schemas, generating metadata that is consistent with the new dataset, generating validity rules or policies for the new dataset, and more. Let's take a moment to cover the lessons and topics in this module. Welcome to this module on data transformation with generative AI. That is, how to use GenAI for data operations that involve changing the structure or the schema of an existing dataset. What is going to be our main focus in this module? Well, for example, it's how to detect schemas in datasets if we don't have that information yet, and how to convert those datasets when we need to transform data at the end of the day. So finding out what is the target schema that we need to transform the dataset into and actually carrying that out. Or for example, how to both generate metadata for existing datasets, but also ensure that the metadata that we have will remain congruent across new repositories, or if we change the dataset and we have to change the metadata with the same terms and definitions. In other words, we can have different terms in different metadata repositories. It's not just about the existence of metadata, but the congruence of metadata, and doing this with GenAI. Or for example, how to generate rules that dictate the requirements for data validity, as well as policies such as data retention policies or access control policies, and localizing these for specific apps or repositories. In other words, cascading down the general data validity rules or the general policies to specific repositories or specific applications to translate them into specific infrastructure, if you will, going from generic to practical. In this module, we are going to have 3 main lessons for this purpose. The first lesson is about schema conversion and mapping. It's about using GenAI to actually convert a dataset from one schema to another schema, for example, mapping specific fields and converting formats of specific fields. It's about finding out what is the source schema, what is the target schema, what is the mapping between the two, and actually carrying out that transformation. Then, lesson number 2 is going to be about metadata generation and consistency. That is, using GenAI to document existing datasets that we may have in terms of fields, policies, sensitivity levels, and other characteristics that are worthwhile to note down in terms of metadata and ensuring that those metadata remain consistent across various repositories. Again, same terms and definitions for all metadata. And lesson number 3 is going to be about validity rule and policy creation. That is, using GenAI to automatically calculate what are the rules to enforce the validity of that dataset in order to have high data quality. For example, we need a certain value for this field, this value must be within this range, and so on, but also defining the general policies that may aid us in a variety of areas, such as data retention policies, access control policies, and so on, and translating those to specific applications and repositories. For example, if we have a general data retention policy to keep data for 90 days maximum, how do we translate that to a specific web application that we may have, to a specific mobile application, a specific database, and so on, taking the theoretical and making it practical. So as you see, this module is going to be all about data transformation, how to use GenAI to help you take one dataset from a specific format to a target format. Let's talk about using GenAI to help you with converting schemas and mapping fields. This is the traditional use case, if you will, when you are transforming datasets. You have a source schema, you have a target schema, and you need to map the fields between both so that you can perform the data conversion. But in certain cases, you don't know the source schema, you may not know the target schema, and you then